Good morning, everyone. I hope you're all doing very well. Ready for day 2, where we will have a session on embedded ML and later IoT. So I'm not sure whether our facilitators are online. I can't tell from the names. Maria, are you on board? Oh yeah, I see Anani. Good to see you. Anani, how are you?
Hey, everyone. Can you hear us?
Good. Yes, I can hear you.
Perfect.
I'm hoping I speak for everyone, but I think people can say on the chat whether they can hear.
Okay.
Okay, great. So I think maybe you can try and see if you can share your screen, because we'll hand it over to you immediately so that we can start exactly on time.
That's fair.
Right.
Then I was setting up the presentation. Oh yeah.
Sorry?
I was setting up the presentation.
Okay.
Just logistics. This is quite a crowd there.
Well, it should be building up. Yesterday we had up to 90.
Wow. Yeah.
So hopefully people are on the way. There's a bit of an echo from your side.
Yeah, we're having two computers. Mute.
Yeah.
Test. Testing again. Huh.
Yeah, still a little bit of echo.
Testing again. Oh, I see. You connected to the. Oh, you can. Is this better? Yeah. So yeah, now this is better. I think we were set up a projector so we could see the screens.
Okay. Okay. Now it's much better now.
Okay.
All right. So I'm very happy to that you made time. I don't know. I don't dare ask what time it is where you are.
But it is 2 a.m. So if we slow our words, please apologize. We are just downing a lot of coffee now.
Okay, then over to you. Introduce yourselves and thanks a lot.
Thank you for having us.
Yeah, that's they can share screen.
Okay. Can everyone see our screen now?
Okay. Can everyone hear me? Can you hear me? Okay, cool.
Yeah, yes, I can.
All right, nice. So hi everyone, my name is Maria and currently a PhD student at Dartmouth College. And this is Anani, he can introduce himself.
Oh, yeah, my name is Anania. I currently work as an embedded software engineer with a local startup here in New Hampshire.
Yeah, so today we have the huge pleasure of briefly talking about embedded systems and machine learning, specifically machine learning on embedded systems. This is something we're both really interested in, and we're excited to present this work to you. So we have a brief outline of how everything is going to go. Anani is going to talk about the embedded systems portion, give you a brief overview of embedded systems, really what they contain, how they work, what are their limitations. And then I'll cover the tiny ML portion, which is the machine learning portion, specifically for embedded systems. And we'll give you a bunch of resources that you can use later to explore more in this area. Lastly, we'll have a demo using Edge Impulse. So if you guys got the Google Drive document yesterday, I hope you set up accounts. If not, we can still do it today. So, and then you will start.
Awesome. Before we proceed, I just want to check that folks were able to install the Arduino software. If not, this would be a good time to try it because it takes quite some time to load up. In the link that we provided, there should be instructions on how to access it. Right. I'm just loading up my notes. A few seconds. All right. So yeah, what is an embedded system? An embedded system is basically a computer that performs a computer system that performs a specific function, either independently or as part of a larger system. They have kind of taken over and are everywhere in every place in our life, from a microwave oven to a smartphone that you may have, to even a traffic light or smartwatch that you currently have. One example of embedded system that we can just look a little bit deeper in is an analog and digital camera. Some of us are old enough to know about the traditional old school cameras with these things. This was basically an optical system, optical mechanical system. And with the development of embedded systems, we're able to move that to a fully digital system that you see on the right here. And what really makes it digital is, and an embedded system is really the microcontroller and the processors in place that let you still essentially perform the same task as the old school one, but with the digital computer added, it just adds a lot more functionality to it. Just a quick historical note. The first notable embedded system was really used in the Apollo mission to the moon in a system called the Apollo Guidance System. And this was the groundbreaking way of using computers to process a lot of inputs from multiple places in order to be able to successfully perform this mission. And in the 70s, we got the first really commercially produced microprocessor, which was the Intel 4004. And this was really groundbreaking and started getting more into the common day-to-day lives. And from that point forward, it just exploded. Just a quick fun fact that I want to share here. Nowadays, with a standard $70 Bitcoin mining USB flash drive, you can compute about 130 billion hashes per second. And how many would you imagine this initial microcontroller allowed to compute? If people had to guess, what would people say? How many would you think the old computer in the 60s could compute in 1 second, given that nowadays we can do 13 billions? Oh, I guess in the chat, we can also do in the chat actually. Yeah, let's do chat. Can people type their answers or guesses in the chat? One of the goals also is just to make this interactive. So ask any questions you may have. So someone said 100,000 in a second. That's a noble guess. Now someone actually went and tried to run Bitcoin mining software on that old computer, and it took them 10 seconds for one single hash. So if you're trying to mine Bitcoin with that computer, you probably will not be able to make any money at all, even if you're given all the time the universe has been existing. So this is really how far we have gotten in terms of computation prowess in these systems. So yeah, the key components of an embedded system are what they say here. You usually start with an input to your system, your processing unit, interfacing with some application-specific circuitry, and finally putting out the results of that processing and service to an output system or a communication interface. I will start by taking a deeper look at the input system, and this is usually driven by a lot of sensors, and sensors are really what allows us to measure and interface with our surroundings. Before you start any embedded system, you usually need to figure out what type of sensors you need in your system to be able to solve the application that you want to address. And in that field, there's a lot of sensors available nowadays, from sensors that let you measure temperature to sensors that let you measure real-time concentration of gas, or even sensors that measure light. One interesting one is one that measures moisture in soil, and that has been used a lot of times in things like agricultural embedded systems. And finally, I wanted to draw special attention to the sensor at the bottom row here, the touch sensor, which basically in 2007 with the iPhone popularizing it, that really opened up a new world of smartphones that really revolutionized the way we interface with an embedded system that was the smartphone. With the way Apple implemented it, on the advancement they did in the sensing technology there, touch sensing, it just opened up a new world of what is possible for us. So yeah, moving on to the next part of the system, usually the outputs, and this is really where you present the result of your processes to the end user or end system. And usually you have a display, or it can be an LED that blinks a certain code when an error happens, or being able to take an action on the environment. For example, if you have an embedded system that controls air conditioning, will turn on or turn off the AC, or even move the robotic arm of the rest of your system. And next, we have the application-specific circuitry, and that's really where you build the additional hardware needed for your system to operate things like your battery circuitry, any other external interface to other third-party systems that you want to have. But we'll focus specifically on this top range here, from the CPU to read-only memory to random access, because that's really the heart of the embedded system, and that's what does the heavy lifting. Processors in general can be split into two groups. You have application-specific processors that have been explicitly designed and developed for a specific application. Those are usually expensive to develop, they're expensive to maintain. Just in terms of the talent you need to be able to build a processor from ground up for a specific application. That was the use case of the processor used in the Apollo mission. It was developed for that application that took human beings to the moon. But nowadays, we're lucky that there are a lot of processors out there that are general purpose, and that's really the second group. And we'll focus specifically on the microcontroller. And you can think of microcontrollers as computers on a chip, and usually get them off the shelf. They are really small sized. They're really low cost depending on what you want. And there's such a wide variety of microcontrollers out there that you rarely have to go outside of that group to get an application specific processor. So yeah, breaking out a microcontroller into its key elements. Here you have the input and output peripherals, and that's really a way for you to interface with the rest of your hardware and the rest of your system. For example, we have an input that turns on an LED. That's what you connect your LED to the input or to the output part of your microcontroller. Next one is the read-only memory or your flash memory, and that's really where you store the software data and you store your code and any data that's needed for operation. And here we usually talk in the kilobyte to megabyte range, so not a lot of memory available, and that really controls how complex your software can get and how big it can get. For example, if you have a lookup table to speed up one specific map function, you need to be aware of that because the amount of memory you have available for that lookup table may be limited by the type of microcontroller you use. Next, we have the CPU, Central Processing Unit, which is really the brains of the system that executes the code that you've written. Code that's compiled in machine language from higher level languages like C or Python that your microcontroller can execute. And next, we have the clock, which is really controlling how fast your microcontroller can run and how fast it can execute your code. When we start looking in the embedded machine learning part, you'll see that this is important in how what kind of latency you can get in your application. And this also controls how much power your system will use, depending on the use case. And finally, we have the random access memory, RAM, which is another kind of memory that basically stores temporary data that your code needs to have access at runtime, and that doesn't necessarily need to persist after power cycles. Any questions so far? Feel free to type your questions on the comment section and we will go over them as needed. All right, so now for this particular application, we are looking into a development board called from the Arduino interface. It's quite a popular one and a lot of people have had the chance to play around with that. So this is what we'll be using for the workshop next following minutes. So here, really, these are really ways to really simplify the prototyping phase. And even when you get to a production stage, you can usually start your production design from these development boards. Let me quickly open up the data sheet of one of them so you can really see how to usually approach these microcontrollers and what really is important as you're evaluating those. So most embedded applications require low power because they're usually in situations where you don't necessarily have access to full outlet power or you running off a battery. So the lower power your system is, the better it will be. Some are directly plugged into the wall, so that's not too big of a concern, but still, that's something you want to be aware of. The architecture here really controls the kind of performance you can get out of your system. In this particular processor, we can get 20 MIPS. This is million instructions per second when you set up your clock to run at 20 megahertz. And just for comparison, most laptops have clocks that can run at gigahertz, like 2 to 5 gigahertz. So it's a whole other magnitude scale, a whole other scale above what you usually, below what you usually get on the computer. And below here, you usually have details about the memory system that you have. You have all kinds of memories that you can have access to and the amounts that you can have. And you can see really the amounts are really limited to the range of kilobytes in this particular microcontroller. And interestingly, you also limited in how many times you can program and erase those microcontrollers memories. So that's another parameter to keep in mind as you're looking to develop software to run on these. And data retention usually on those is 20 years and up. And there's usually also a temperature gradient that your system needs to obey to. Finally, peripherals are really important because basically if your microcontroller already has a peripheral, then you don't need to add it external to what the microcontroller already provides. That really reduces the cost, reduces power consumption, and makes your system more reliable because you no longer have multiple moving parts or multiple chips that you wanna manage there. Let's see something else here. Wanted to get to, yeah, so operating conditions. This is really where, depending on where your application will go, it is important to know about those parameters. So this particular controller can operate from -40 Celsius to 85. There are controllers that can go well beyond these ranges, but that really depends on the application your system is going to be used in. If you're trying to measure, design a system that will measure air quality around volcanoes, you'll probably want to get something a little bit higher rated than 85 Celsius. And finally, we have the power consumption section, which really tells you how much power your system will be using per second. And this really gives you an idea of how far you can push the system and any restriction you may want to have your software follow as you're designing it. All right, going back here. So yeah, so the software section of an embedded system basically is what encodes the process that you want your application to follow. And it's often called firmware, in that it's software that's really running directly on the hardware with really not a lot of layer of abstraction between the software and the low-level hardware. And most of the time, embedded C is by far the most common language used, just because of how close you can get to the hardware and what type of optimization you can really perform. We'll see a few examples of that in the as we go through the presentation. But other languages are also used. C++ is really common. Nowadays, a lot of people using some Python for embedded systems. And that's usually important when you start talking about machine learning processes. If your system already runs in Python, maybe you may just stick with it there, but that requires usually a much more powerful microcontroller. Assembly is super rare. That's really essentially talking machine language directly, and that's as low level as you can get. That's usually challenging to maintain long term, but in systems that really require high performance, assembly is usually what people do. What's common is you'd use embedded C, and then some of the functions that you really need to optimize precisely, you will compile that and write your own assembly to execute those. And finally, for people familiar with web development, there are some crazy folks out there using JavaScript for embedded systems, which is impressive. It's doable. I've seen some systems that use it, and it's usually in cases where you have a much more powerful microcontroller and you want to limit the amount of languages that your programmers need to support and maintain long term. Any questions?
Yeah, there's one question. So, which programming language do you recommend for data scientists to use in embedded systems?
That's a good question. The most of the time, embedded system data science is usually done in Python nowadays. The microcontrollers that can run Python natively without any gymnastics are usually much more expensive. If your application allows it, then it may be simple to use Python. But when you're deciding on a language, it's really trying to decide between cost of your overall system and also the long-term maintenance. Because you write the software, you'll need to support it, you'll need to continue improving it. So usually you want to pick something that you know you can have the talent to maintain it long-term. So if you work in a team where everyone already knows Python and you don't have access to a lot of embedded C experts, then it may make sense to design your system to use Python. But by far, embedded C is usually one you at least want to consider for embedded systems, just because of how available tools are to build software using that language. That makes sense.
Oh, someone says they can't hear you.
No. How is our audio now? Can people hear us now?
Oh,
Oh, okay, might have been on someone's. Okay. Okay. Yeah, those are really great questions. So addressing the first one about performance difference between those languages. So by nature, if we go back to assembly is always going to be the winner because you are literally talking machine language. Whenever you go for a higher level language, you rely on a compiler to take, for example, an operation you're trying to do and transform it into what it thinks is the best approach to executing that. So in situations where you know better, you can go directly assembly, but that's really rarely done. But C usually will be the closest to performance on embedded systems. On a computer, you're writing your code in C versus Python, the performance differences may not be as significant, but usually what I've seen is people write Python code, feed it to another software that will transform it to machine code that will execute. So part of that transformation will really be, you'll be losing in efficiency that you would not, you'll be losing efficiency essentially. So I'd rank it that way: assembly, embedded C, and then those higher level languages, because they usually need to have a higher level compiler to transform them into runnable code. And next question was the difference between embedded C and C. This is really where embedded C is not, that's a tricky one. At a high level, it's essentially the same language, so you don't need to learn a different language or anything like that. It's just some of the functions and processes you use are slightly different because now you are in an embedded system. So there are usually standards that you want to follow in an embedded system. For people familiar with C, in an embedded system, you usually don't want to use mallocs to allocate memory. You can, but in embedded C, you usually want to just go with knowing exactly what memory you use and not rely on the dynamically generated processes. But yeah, at a high level, they're essentially the same syntax, but there are a few libraries and programming techniques that are different when we're talking about writing C for an embedded system. Awesome. Yeah, those were amazing questions. So at this point, we wanted now to move to a little bit of practical, just start coding a little bit and demo of what an embedded code looks like in an embedded system using the Arduino platform. So if everyone can open their Arduino IDE, and Arduino is really a platform that abstracts a complexity of hardware design and software design by giving you a really quick way to prototype and experiment with code. So what we'll do here is quickly, let me choose a lot of things. Most of my code is already written, so so if you can open your Arduino terminals and go to the menu here. Can people see my screen well? It's a little bit tiny. Zoom in a bit. So the first thing we'll do is open up the first example. As you're learning a programming language, usually you start with the hello world example. In an embedded world, the hello world here is usually blinking an LED on and off. I can see someone raise their hand.
Pardon me, so I just want to make sure that if everyone has this software open or not, so they can keep up with what you're doing.
Okay, so let me give folks maybe a few minutes. Can open up and comment out, add the comments to let us know how far you've got or if you're facing any issues. So the example we're going to be looking at is found in the example section basics, and then it's called Blink. People. And the nice thing with this Arduino platform is that there's so many learning resources available out there that really try to help people understand and quickly play around with stuff. I think the platform that we have here is the Arduino Nano, which is usually that's the one you want to start with. It abstracts a lot of complexity, and it's a much simpler hardware for you to interact with. But as you start going up and down, there's usually a lot of things you can, a lot of different Arduino systems you can explore. So yeah, just taking a quick look at the architecture of this code. The first section is the setup part, which really is setting up your system. In this particular case, we just say the LED identified by this factor should be set as an output, so it can put some current out and turn on the LED. And the next section is the loop section. In an embedded world, you usually have code that runs forever. So a lot of times you just have a loop that's running forever until there's an error or power cycle. So in this particular case, Arduino provides you a loop function, and this will be called, this is what is called after you set up everything, and it will be called in the loop forever again and never run out. It's pretty common for embedded, in an embedded system to see something like this, where you do while forever, just do something here. So yeah, let's try to compile this code and run it on the Arduino board. And here, essentially, in the loop, you can see the first thing we do is turn on the LED high, wait for 1000 milliseconds, and turn it low again and wait another millisecond. So essentially, this will blink your LED. So I'm building it here. It may take, depending on your system, it may take a few seconds to a few minutes. The manual will take a few minutes. So, how are people doing question-wise? Okay, so for the sample code, you would go to File, and there's an examples menu item here, and we're starting with the basic one, and that's the Blink example that we opened here. If people have been able to build the code or get to it, just send thumbs up in the comment section. Leave a like in the comment section. Nice. Okay. So what now you do is, one other thing, we want to select the board that we're using. In your system is going to be a little bit different. I have a few boards that are installed here. So if you go to your tools section and go to boards, in your particular case, if you go to the AVR boards, there will be our Arduino Uno board there. So you'd select that. In my case, I'm selecting a different board. And before you move on, you want to go and select a port. There's usually going to be only one, so just make sure that it's selected correctly. I will go ahead and use the upload option here to, it usually will rebuild sometimes, or just upload it directly to your hardware. If you have everything powered up, you'll see there should be a green light that's just on to indicate that you have LED, that you have power. But then once the code is loaded, you'll see the LED start blinking. In my case, I can actually start seeing it happen. How visible is it? I don't have that.
You can hardly see it.
Can you hardly see?
Oh no, I can see it.
Okay.
That's good.
So you can see now on my hardware, it's just turning on the LED 1 second at a time. And it will do that forever until power cycle or after reset. For the upload instruction, so usually you go to tools and select the proper board, Arduino Uno in your case. And after that's selected, go to port, and you should see some ports available there. If you don't see any port, there's a push button right on the Arduino itself. Press that one and it will reset itself, and the port should be available by a computer. Yeah, that is fair. On a Linux system, it's going to be a bit tricky. I should have prepped for that. There's usually some low-level trickeries you need to do to get the parts to show up properly. Yeah, I should have an example there. Let's see. How are people doing? Yeah, let me open up another code that we can take a look at with just a little bit more of an example here. We'll make all this code available. Let me actually copy this whole thing and paste it in the shared document so we can execute that as needed. So let's add this here. So yeah, so we'll provide all the documentation and files needed at the end of the presentation so we can export a little bit more as needed. So if you don't see the port, usually try to press the reset button and your computer should try to identify the port. And so in the code that I just shared, that's a little bit more of a complicated example. The first thing that it did is create a function that I called blink LED, and it's exactly the same one that you used. That was in the basic example. I just extracted that to its own function. So the code can just read a little bit better. One other thing that I've done in the setup here is
Where did you share it?
I've added it to
The Google Drive.
the Google. No, in the document. Let me actually paste that. Oh, I could paste the code in the comments. Look at me. And here's the code. Something, the part is disabled or unclickable. Huh, that is unusual. Yeah, this is another thing that, okay. Yeah, so let me also move with the other demo so people can see the example code there. But usually for embedded design, usually because of how low level you're working with, having computer to hardware issues is not uncommon. So you just brace yourself for it. Arduino in general is really good at providing you instructions and troubleshooting techniques. So for all the issues that people have mentioned, if you go to the Arduino website, they really have a good support section. And the Stack Overflow support for Arduino is just glorious. It's amazing. So yeah, in the code that we have here, we have essentially what we do. We initialize what we're calling serial. And that's essentially a way for me to open the terminal here, serial monitor, they call it, and get some messages from my Arduino system. So I can print, in this example, you can see I'm printing a message here. And I will be able to see that in my serial terminal. So it's a quick way for you to interface with your Arduino system, and more importantly, print some debug lines. So as you are going through your system, you can have debug lines to help you troubleshoot everything. Let me run this example, and you can see how this works. So we initialize the serial terminal just to be able to communicate with the terminal on my computer. And I check every time if I have anything available in the serial terminal. If I have nothing, end the function and just try again forever. But then if I have something, I basically tell my serial terminal to extract any integers from the input that I've given it and store it in the function that I'm calling blink count. Right here, I'm printing something to my terminal to let it know that I received something, and I also print the count that I inputted. And finally, here I just have a loop that basically counts, given the number that I inputted, it basically will go through and print these messages and blink my LED that amount of time. So this is a quick example that basically will just, I'll open it. Let's see. Let me now start loading up this code. Okay. Yeah, unfortunately, so you have to, your computer will basically build the code and load it up to the Arduino, and that's when you'll be able to see the code in action. I imagine there may be some emulators out there that people have put together that let you simulate how it would behave, but usually that's the process here. So and show the LED here while I input some numbers.
Okay.
So what I'm doing here now is I'm opening up the serial monitor. Output. So here, in theory, so if I put a number, let me put 5, I send it. You can see now I'm getting my input, and you should be able to see the LED blinking 5 times. Let me do 10. So essentially, I'm basically letting my microcontroller know with whatever number I give you, blink the LED that amount of times. What if I give it something that's not a number? The system will freak out and say, I received not a number, and it defaults to 0. That's one quick point too for embedded system, because a lot of times it operates outside of your control. You want to practice defensive coding for any weird inputs or any situation your system is. You want it to be able to recover gracefully. For example, for the computers they use on the Apollo mission, you don't want your application, your software to fail and not restart if the input that it got doesn't match expectation, because you're sending that thing in space. You don't know what the sensors are going to do. So you build your code with enough redundancy. So if this happens, catch the error, log it somewhere, and gracefully restart. So you can always have something going. Let me see. Oh yeah, that's a sweet one. So yeah, there are a bunch of, I guess, yeah, there are emulators out there for to be able to see how your code would behave if you don't have the hardware available, or if the hardware is acting out on your computer. But yeah, I think for interest of time, we'll move on to the next section, which is really the juicy part. That's where we dive into the machine learning part. This was the old school way of doing things. So if I go back to the presentation, oh, I think that's good. So yeah, so what we've done is just quickly overview of how a program looks like in the Arduino interface. And this is also using C. And we've built a custom program that basically takes an input and blinks the LED a number of times. We wish we had more time to really go around and make sure everyone was successful. Was anyone able to run the code on the board or get the blink example working? If you were, please. So yeah, if you get the example working, let me know. And let's see. So yeah, moving to the next section. So yeah, what we've been able to with the old school way, embedded systems usually have limitations. And the first limitation a lot of people talk about is cost. Because these are devices that you're going to be deploying usually in the thousands or even millions. Even saving a fraction of a dollar makes a big difference in your bottom line. So cost is a big one. But nowadays, there's a lot of open source solution or system on a chip available for speeding up the development process and thus reducing costs, or even at the production line, you no longer need to build your own custom system. Deployment flexibility is also one challenge. They're going to be installed in all kind of places. So improvements in batteries have made a big difference. Even energy harvesting, from harvesting solar energy to other ways of collecting energy to run on these, and even in improving the robustness of the hardware so they can be run in more extreme environments. Finally, you also have improvement in network and information extraction. And this is really where IoT, Internet of Things, comes into play. Back in the day, you have those independent IoT devices all connected to a local network, but how do you get that information out of it? IoT is making a big change there with new network protocols or even mesh architecture where we have IoT devices talking to each other, and finally to the internet. And lastly, one limitation is computing ability. So the type of code and smart you can get your system was limited in terms of because of the processing available on your system. And this is where IoT and in general TinyML come into play. And this is a nice transition to the juicier part of the presentation. So how do you want to do this?
Share my screen.
I'll monitor the chat for questions. And yeah, if you have any questions, just keep sending them to the chat. We'll address them as we go. I can see your screen.
All right. Okay, so before I start TinyML, I'm going to just give a brief overview of IoT. So IoT, which is the Internet of Things, revolutionized the way people use embedded systems. One way is that now you have these like tiny embedded systems placed throughout the area, and they connect to like a central hub. And this hub is connected to a cloud server. So you have the availability of cloud computing services to do your programming, right? So now you can send your data from the embedded system to the hub and then to the cloud server. And then that does the processing for you and sends back a response to the user or back to the embedded system to make any changes. This was really great because now you could, sorry, let me get this going. So an example is like an Alexa device. So when you send in a response to Alexa, Alexa sends the request to a cloud server in, somewhere in the US. And that cloud server does all the processing and then sends a response back to your Alexa device, and Alexa repeats it back to you. So this is like a typical application of an IoT device. So This is hugely beneficial because now you have cloud computing services at your disposal. Cloud computing services provide you with lots of computing power. So remember how Anani talked about having megahertz on your embedded systems. On the cloud, you'd have gigahertz of computing speed. You'd also have lots of storage space. So you'd have gigabytes of RAM that you can use to store all your data. And these two things, like the huge computing power and the storage space, make it easy for you to scale up. So you can add more embedded systems to your local network or to your hub or to your cloud server if you're connecting it directly. You can remove old antiquated systems. This also helps you streamline your software and your firmware updates because now you have one central hub and you can just dispose of it easily. And so that was a huge benefit of cloud services, but there were also some limitations. And one of the limitations is that now you require a constant network connection. So if you're using internet, you need to be connected to the internet reliably to use this system. This isn't great if you're in a place that has unreliable network, which I grew up in. Additionally, your systems become power hungry. Now, you're sending data from your embedded systems to the cloud frequently, and this drains so much power. So if you go back to your Alexa device needs to be plugged in to work because now it's sending all your instructions directly to the cloud, and without being plugged in, it's not able to do any of that. So it's very power hungry. So one solution people used to fix how much data is sent to the cloud is like they reduced the form of the data. So they kind of reduce the dimensionality. And in that way, you're losing data at the embedded system level. So if you're sending an average of your data as opposed to like using your raw data, you're going to lose some important information in that process. And also your system is prone to security attacks. So if you have one central system and it gets attacked, that's like terrible because then you'd have to like stop everything. I guess it's also good because then you can fix one point as opposed to multiple points. And lastly, because you're sending your data to the cloud, there's privacy concerns, especially when it comes to confidential information or healthcare information. So TinyML is kind of a solution to these cloud-based limitations, but not really a replacement. So TinyML kind of works hand in hand with IoT to address some of these issues. And that's where the TinyML discussion begins. So what is TinyML? TinyML is basically trying to build machine learning algorithms and optimizing them so you can deploy them on these small resource constrained hardware devices. So your hardware device has limited computing power, it has limited storage, it has low speed, like how fast the computations can run. It has all these resource constraints, and you're trying to build a machine learning algorithm which is resource intensive on these tiny devices. So that's what TinyML is, trying to figure out how to map that. Going back to the Alexa example, so where TinyML would come in is that now you no longer need to send your request to the cloud, or if you do, it would be like a minimal like thing. So you would send your request to Alexa. Alexa does the computation on edge and then sends your response back. So you no longer need to send your data over the cloud. So that reduces your power requirements. It gives you some privacy of your data because now it's just localized to one device. You can use all your raw data because you're doing your processing in real time. And so there's no need to also reduce its representation. So you're using your data more efficiently. And you don't need a reliable connection to the internet or to any network. So you have more freedom in your design. So these are some of the benefits of TinyML. Because of the way TinyML has grown over the years, it has so many applications in industry. It has applications in smart retail, so personalized shopping. Some companies like Walmart are starting to use personalized shopping to do to improve. To improve how people shop. personalized healthcare. So if you have a smartwatch monitoring your biosignals, that's another use of TinyML in real time. So these things are helping people detect illnesses, predict your ability to get sick in the future based off of your current biosignals, being used in smart manufacturing to do anomaly detection, precision agriculture to improve the outcomes of your farming practices or your cows. Like a nice company that's doing precision agriculture using TinyML is Imagimob. I don't know if any of you have heard of it, but it has these necklaces that it puts on cows and just monitors how cows are eating and grazing and doing all the daily activities so it can better optimize feeding and different structures of that. There's autonomous driving. We're using TinyML in autonomous driving and smart homes efficiently. So how would you build a TinyML application? To start, there's 3 main considerations you'd need to think about when you're building TinyML. The first one is your latency requirements. I'll go over these in more detail in the next slides, but I just want to point out the 4 considerations you need to think about. So you need to think about your latency. You need to think about your memory usage, what computing resources you have available to you, and your power consumption. These 4 resources are characteristic of the embedded hardware that you're using. So you look at your data sheet that Anani went through and figure out what you would need. So let's start with your latency. So latency basically describes how long you're willing or how long you have to wait for your algorithm to give you a result. This is in IoT devices, this was usually limited by transferring data to the cloud and waiting for it to send a response back. But TinyML by design reduces your latency by a huge amount, but you still need to consider how long you're going to spend before you can get an answer back from your algorithm, right? So an example is if you have a sampling rate of 300 hertz, so that means you're getting 300 samples every second, and you want to do analysis, like a time series analysis, a sample at a time, what would your maximum latency be? So you just have your sample at a time divided by the frequency. And so that means every 3.3 milliseconds, your algorithm should be complete with its processing. That's from when you sample the point and then you get a result. It should be less than 3.3 milliseconds. So now if you're processing on 50 samples at a time, your latency can increase because now you have a buffer and you're storing in 50 samples, and then you divide that by your sampling frequency. And so you have 166.6 milliseconds for your algorithm to run before you process another 50 samples, if that makes sense. Does that make sense, guys? Okay, I'll assume yes. So I do have a small quiz on these latency requirements that I'm going to ask you guys to do. It's just it's 2 questions. So this is the quiz. You can post your answers in the chat.
Someone had a question on, as an embedded engineer, you need to be good in both hardware and firmware development.
I'll say yes. Yeah, it would be good for you to be proficient in both. And it always depends on, like, I guess, what you're trying to do long term. If you want to stick mainly to hardware, then there's no need. But if you want to just be more versatile, yeah, definitely.
Yeah, I work at a company here where I am the firmware engineer primarily, but I've taken some courses in electronics so I can talk with the hardware engineers and understand the challenges. I can design some systems. So you don't necessarily need to be an expert in one or the other, but you need to at least know a little bit about the other so you can interact well with each other. Got some questions coming. Can I answer too?
Yeah, definitely.
Select E, all of the above. Does latency depend on network speed?
In this particular situation, it depends on your embedded system, because now you're localizing your neural network to work on the edge device. So like on your hardware itself. So your latency will be based off of like how fast you're sampling your data and how long it takes your algorithm to run. And so you want to minimize how long your algorithm takes to run. That makes sense. Okay, so thanks guys. Those who answered, thank you. I'll just go straight to the solution. So for 1, it's A, and for 2, it's B. So if you have a sampling frequency of 5 Hertz and you're sampling 1 sample at a time, your latency is going to be 200 milliseconds, because you need 200, you have you have 200 milliseconds before your next sample comes in, basically. So you want to be done with your processing by then. And if you have a sampling frequency of 16 Hertz and you're doing a sample at a time, your latency decreases a lot to 62.5 microseconds. So you have to run your algorithm way faster than this. So if you have such a system where you have to process 1 sample a time for 16 kilohertz, you could think about averaging to reduce your latency requirements, or reducing your sampling frequency if you don't need such high precision. Okay, so I'll go to the next slide then. The next topic is memory. So running your memory, when you have memory on your IoT device, you usually have the cloud memory resources available to you, and that's in gigabytes, right? So you have gigabytes of storage at your disposal. On embedded devices, you have kilobyte to millibyte range memory available to you, basically. So now your model has to be really small, so you have to, like, if you had millions of parameters in your original design, you have to reduce that by a lot. I'll give you an example here. So the TensorFlow Lite micro speech model uses about 14 kilobytes of RAM to run, and the embedded group, which you can find at this reference, it does cough detection, and it's about 3 kilobytes to run. And these are deep learning models that are running on an embedded system. So now you need to take your algorithm from like megabytes, hundreds of megabytes, to kilobyte range for memory, so it can fit in your actual device. This is something you need to consider when you're doing your tiny ML design. Another consideration is your computing resources. So how fast does your embedded hardware run at? So this will affect your latency, and it will affect how many computations you need to run, affect your memory requirements as well. So this is important to look at. Does it have a digital signal processing hardware available for you to use? This could optimize some of the signal processing that you're doing to your data. Does it have a floating point unit available to you as well? This could help you if you decide to use floating points instead of integers. This could improve latency for you. So these are some considerations you can look at when you're picking the hardware to use. Power consumption. This is important, especially because if you want your embedded hardware not to be connected to a wall outlet, you need to think about how much power it's consuming. One way is to minimize your latency, so you can switch to sleep mode, and that's where you make most of your power savings, is in sleep mode, by having your device run in sleep mode. So reducing how many computations you have. Another way is you can use TinyML as a wake-up circuit. So if you have your IoT system, you don't need to have it be live all the time. You could just implement a TinyML wake-up circuit in there. And then when it detects an activity or something, it could just turn to your IoT system then and then wake it up, and that could reduce your power consumption. So in this way, you're using TinyML really as a way to reduce your power consumption. Yeah, so in summary, when you're designing your TinyML algorithms, just make sure to think about your latency requirements, how much memory you have available to you, what computing resources does your hardware have, and what are your power requirements. This is something you'll measure experimentally once you're done building your design, but just think about these things when you're starting out. So I'm going to tell you about 3 techniques you can use to optimize for these considerations I just mentioned. And the 3 techniques are pruning, quantization, and distillation. So I'm calling them destructive techniques, and this is a term used by a researcher at Cambridge. And the reason I'm calling them destructive is that you basically build your machine learning model and you have it working, and then you add these techniques to kind of dwindle it down, as opposed to building it. Constructive is when you like start from the beginning and you're making it small, right? So you're building it small and adding layers to improve its performance, as opposed to building it big and then trimming it down so it can fit on your device. So I'll cover these 3 techniques right now. So pruning. What's pruning? So pruning it's kind of like the agriculture lessons we took in high school, where farmers have to cut out like the bad or diseased or like old parts of a plant to enable the rest of it to grow. So that's kind of like what pruning is. You want to take out nodes and connections in your model that don't really contribute much to your design. And in that way, you're making it more making it use less space, and you're making it more like efficient to deploy on a TinyML system. So why would you prune? As I mentioned, right? So when you're developing these machine learning models, it's like trying to find a needle in a haystack. So to increase your likelihood of finding that needle in that haystack, it's common for people to build these deep neural networks, and they'll be overly parameterized. So you have lots of parameters in there. And because of this, the large models do perform better on like various tasks, right? So it's good to build your large models initially. But what happens though is that these models require a lot of storage space. In order for you to save your weights, they require longer time to run, to also train. It's just tedious to do that. And if you're going to implement it on an embedded system, you may end up buying an expensive one just so you can fit these huge models, and that may not be necessary. So this is where pruning comes in. What pruning does is that what they discovered is that you don't need all these connections that you have for your model to like run. You can actually remove some of these connections and they're redundant, and have a sparsely connected model that still gives you the same accuracy, right? So what it means by removing the connections, you're setting those weights to 0 basically. And so you have a less connected network. And that's what we call weight pruning. So weight pruning is setting like some of these weights that you see to 0. So in this regard, you like have less connections going to the next layer and to the next layer and to the next layer. And this makes your model more efficient. So that's one way of doing pruning. The next way of doing pruning is node removal. So node removal, you're basically removing some of like the actual neurons / nodes in your network. And the way to understand it is if you have a node that's doing the same thing or something similar, has similar weights as another one, you want to get rid of it and remove the redundancy in your system. This is a little bit harder to do. So most people do the weight pruning, but it's an option available still that you can consider. And your final network would look something like this, right? So now you have sparsely connected models. You've reduced your model size. You can have it run faster than before because now there's less connections. But the one disadvantage is that there may be a slight decrease in accuracy, but it's only going to be slight. So if you have 95% accuracy, you may go to like 94.9% accuracy. And you need to check these also. Yeah, so I'll give you a quick example. In this paper, all the references will be included, so you can like go read these papers as well. They use the VGGNet on ImageNet and AlexNet on ImageNet and performed pruning, and they saw a 13x decrease in the size on the VGG 16 and a 9x decrease in the size on the AlexNet. And this was like with no decrease in accuracy on these systems. So how does pruning work? So pruning starts from a pre-trained model. So you train your model and you get good accuracy that you're fine with, good performance that you're fine with, and then you run this pruning layer. So the pruning layer just goes over your pre-trained model, figures out which networks can be set to 0, right? Usually it goes by the weights that are closest to 0 and sets those to 0, and then just starts training it and seeing how well it performs. And you can have it set to be kind of like go from 50% sparsely connected to like 80%. And I'll show you an example of that real quick. But yeah, you can just train your network to remove some of the connection it has and make sure it maintains the accuracy or close enough accuracy that it had as a pre-trained network, if that makes sense. Another one would be you prune your model and then you train it again from the beginning. This is obviously more tedious and you probably want to avoid it, but that's also like a way to do it. So pruning is like an iterative process. And it's done once you have your pre-trained model that has ideal performance. So I will go to Google Colab now to do a quick example. And this link is in the Drive, the Google Drive document. So you'll be able to access it. I will open it in a second. Can you guys still see my screen? I hope so. Okay. Did you put it? Okay. Okay. Cool. So everyone can see it. So I use TensorFlow for most of my coding. So I'm sure PyTorch has a few examples, but TensorFlow has this amazing example that you can take a look at and has lots of resources for pruning. But in this particular example, we're using the MNIST data set that we load in here, and then we build the model. So this model has 20,410 parameters, and then we train it and get our accuracy that's required. So here we have an accuracy of about 95%, right? So that's how we've done the pruning for this particular section. So this is our baseline model, and now we're going to prune that. So we set, TensorFlow has like this cool optimization functions that we can use. And I'll encourage you guys to like take a look at these and see how they're working. So we set up our prune function that we're going to run, determine all like the batch size, the epochs, the split that we would need for these. And then here we set our pruning parameters, right? So now we're setting it from 50% sparsity to 80% and how long it should run. And then we build our model here using this optimization function and then run it. So this is a summary of that. We just have a few pruning parameters that are added that's going to like help us optimize our model. And then we'll run this. This was run for 2 epochs. And you can see that the validation accuracy and this didn't change much, right? So if you look here, after pruning, we have a test accuracy of 95%, 95.18%, and the baseline was 95.35%, right? And so this is just saving the model and getting the size. And so when you look at the size, we went from the baseline that was 76 kilobytes to now 25 kilobytes. It's about 3 times decrease in size using pruning alone. that's like huge in TinyML. So if you can definitely get more, like I said here in the VGGNet, they had like a 13x decrease in size, and the AlexNet, they had a 9x decrease in size. So that's one quick way that you can apply pruning. And this is essential, not just for TinyML, but for any like code that you're developing for your future use. If you're doing some IoT cloud-based computing, definitely think about using pruning to just bring down the size of your network. That will increase the inference. The next technique I'm going to discuss is quantization. So can you see my slides? Right, you can see them? Okay. So quantization is a commonly used technique, especially in traditional signal processing. It's basically a method to map a continuous set of numbers to discrete values. And now what, like a common example is rounding. So if you have, say, values from -1 to 1, and you round them to as like the only one decimal point, which is what I've shown in the figure on the left, then you'll have these quantized levels every 0.1 decimal point, right? So it's like a step, every step you're like jumping up. In this particular example, we have 21 levels, which means you can use 5 bits to represent those. And you'll still get like a good approximation of your original signal, so of this original sine wave. You can then take it to a more extreme point and use 7 levels to represent your sine wave. In this case, you'd need only 3 bits to represent that, but you can see you lose more precision in your signal. Yeah, so the ability to like reduce, but I guess when you have 7 levels, you're going down from 21 levels to 7 levels, right? From 5 bits to 3 bits, which is a huge save in storage space. But then you're losing precision. So quantization is hugely beneficial to TinyML, but you need to be aware of like the precision trade-off. So I do have another quiz for you guys in regards to quantization. So these are 2 questions for you. Okay, I'll just move forward. So how many bits would you need for 33 levels? And how many would you need for 63 levels? So I'll just go to the answers. For 33 levels, you'd need 6 bits. So this is how, okay.
Nice.
Yeah. Good.
I also had it correct. Proud of myself.
Yeah, so you need 6 bits for that, and you need 6 bits for this, right? So for 33 levels, 5 bits is too small because you only get 32 levels, and 63, 6 bits is just fine. So in this case, I guess what I want to point out is that if you reduce your system to 33 levels, you'll still need 6 bits. So to maximize your, I guess, gain, you just want to switch it to like more gain, get more quantized levels, switch it from 33 to 63 because you'll be using the same number of bits. So that's like something you can keep in mind. I don't know if that makes sense, but it might take time to just like look at it. But yeah, so that's how you get the number of levels that each bit gives you. So the benefits of quantization is that you can reduce your memory usage. So you can go from a 32 bit, which is a floating point, to an int8, and this reduces your storage requirements by 4x. Or you can do it to float 32 to a 16-bit, and this reduces your storage intake by 2x. So another huge benefit of quantization is that you can perform integer operations, right? So when you use quantized, oh, I'm sorry. Sorry about that. So when you use quantization, you can perform integer operations, and these are usually faster, especially on hardware that doesn't have a dedicated floating point unit. We'll see an example of this in a second. You can also use base 2 arithmetic, and this is much faster when you're using like the shifts for division, like the right shift for division and the left shift for multiplication. This is, yeah, so these are much faster to do. So it could reduce your latency as well. So going back to the example that I showed in the VGGNet, so in addition to pruning, they did quantization, and pruning plus quantization gave them a 31x decrease in their model size for the VGG, and for the AlexNet, it was 27x. Yeah, so that's like a real life example of how quantization is beneficial. Like I'd mentioned before, one thing you need to take into account is the precision versus the accuracy trade-off. Heavily quantized weights could lead to a huge loss in precision, which could statistically like significantly decline your model performance. So you just need to be aware of that. One technique is to use quantization aware training, or in the case of binarized neural networks, is to increase the number of layers you have, just to have more depth in your network that can optimize for different what's it called, convex function, convex functions. So these are a few resources that you can take a look at, and we'll look at the Google Colab example. So if we look at the Google Colab example, here I'm using TensorFlow Lite as well. And I'll have links to all this stuff so you guys can take a look later. But TensorFlow Lite, I save the model as a TensorFlow Lite, and I use the optimized function, which will quantize this model for you. TensorFlow uses 8-bit, and you can tell them which kind of quantization you want. 8-bit is usually sufficient. And in this case, when we look at the model size here, the baseline was 76 kilobytes, but the pruned and the quantized size is now 7.97 kilobytes with the same level of accuracy. So I run the accuracy parameters here. And now you can see that the accuracy is still the same, but now you have 10 times the size of your original network, which is great. So you want to think about doing that if you're going to develop these tiny ML algorithms. There's a few resources that you can take a look at. And then the last thing I'm talking about in regards to techniques for optimizing your machine learning models is distillation. So in order to understand distillation, I'm just going to talk about the problem that distillation is trying to address. So most of the machine learning algorithms that are implemented today use deep learning, for example, like the Inception or the VGGNet or ResNet or BERT or any model that you use in your system. And these have good performance on numerous tasks, but they require a lot of storage space. They take a long time before they give you a result. And this makes their implementation very expensive. Another common machine learning category is the ensemble model. So basically you have multiple machine learning algorithms, and then you take an average of their outputs, an unweighted average of their outputs. And this usually has better performance than just one algorithm. So it can be a combination of various models like an SVM or a decision tree. And this takes long as well, because now you have n number of models that you're computing the results for, and then taking the average of that. This takes a lot of storage space, takes much longer. So knowledge distillation is kind of magical in that it helps you reduce the size of these models while maintaining the performance. And this is how it works. So the premise is basically to teach the student, the smaller model, which is called the student, how to perform as well as the larger model called the teacher. And the teacher could be your deep learning model or your ensemble model. So you have your pre-trained network, your teacher network that's pre-trained, and you get your soft target. So those are the predictions of your teacher. And then you have your distillation loss. So you predict the output of your student model, and then your distillation loss is kind of optimizing your soft targets of your teacher to the soft targets of your student, if that makes sense. So instead of the ground truth labels being input to this loss, it's the soft targets of the teacher. So it's kind of learning two tasks. In a way, it's like multitasking learning. And yeah, so that's how distillation works. And this has been shown to work really well. An example is in this paper cited in 2, you can take a look. They use it, they had a baseline model which had about 58.9% accuracy. And then they did 10 different models and took an ensemble average and got 61.1% accuracy. And then when they did a distilled model, just one single model, they were able to get 60.8% accuracy, which was higher than the baseline and smaller than the ensemble. So distillation maintains, ideal performance that your model has. It can maintain the performance of your larger deep learning models or your ensemble models, and yet keeping them small. It requires less storage space and also is able to work much faster than your original large or ensemble models. So take a look at this paper to see how that works. It's quite interesting. And we have an example of distillation as well. This example is like, I definitely play around with it. Oh, we'll go back to this. Definitely play around. Definitely play around with the distillation example. Around the distillation example. But what we do first is to create this distiller class. And this class is basically going to replace your model class that you usually use. So like the model.train, model.predict or model.fit class. And in here, we'll set up your teacher and your student network. And in the compile methods, you have your distillation loss, which will be taking your teacher predicted outputs and your student predicted outputs and kind of optimize for those, and your student loss function. And your alpha is just basically a measure of how much student loss you want to take in and how much distillation loss you want to take in. And these are all parameters that can be decided.
There's a question about what considerations are to be made when picking a teacher and student model.
Oh yeah, so so the teacher model is basically the model that works well for you. So I guess that would depend on the task that you're doing, really. So if you're doing, say, time series, you want to use like a group model. If you're doing images, you want to use a convolutional neural network model that's been learned. So that's all your pre-designed algorithm, right? So you can use any type of network, really. You can try neural architecture search to kind of figure out what network would work best for your particular application. But really, picking the teacher model is like, I guess it's just like a machine learning problem. It's like up to you what model works best. So this is where you like do try and error or do some form of search for whatever model works best. And the student model usually looks like the teacher, but just kind of smaller in size. So you have less weights or less parameters to optimize for, or less layers. And that's basically how you would pick your student. And it's also like a try and error scenario. So you can start with like, say 50% of your original teacher, run it through some neurosearch and optimization. So you can figure out what parameters work well, what temperature you need, what alpha you need. Yeah, if that makes sense. I don't know if that answers your question. But yeah, so you would set up your distiller class that takes in your student loss function. Okay, cool, that's nice. So you take in, so you'd have your distillation loss, your student loss, your alpha, which is takes in both your student loss and your distillation loss, and it kind of weights them. And your temperature. Your temperature basically is a measure of how soft your distribution should be. but distribution I'm talking about is like the teacher distribution and the student distribution. So the teacher predictions may be spiky because it's from a previous neural network, and you just kind of want to smooth those out. But yeah, so that's how your distillation would work. You'd set this up kind of like a multitask learning system, and then you design your teacher network. So in this case, this teacher network that I designed had roughly 1 million parameters in there. And then I designed the student, same kind of model that you have, with fewer parameters, and this is about 20,000 parameters. And then you would train it using the MNIST, you train your model, and then we have 98% accuracy and really low loss. And then you run your distillation. Okay, and then you run your distillation, and as you can see here, we have really low loss compared to what we had previously, and the accuracy is slightly lower, but not by much. And this is much better than if you train it. Okay, I guess this is not the best example, but you can see if you train it just on the student by itself, I guess you get good accuracy as well, but your loss is slightly higher. So yeah, so I guess in this case, it works well, but you can try it on different networks. You can take it down. You can make your student model slightly smaller. Your student model here slightly smaller, and see how that actually pans out. You'd have higher accuracy in your distillation model than your student model trained from scratch. And those are some of the results we've seen in papers. So yeah, so sorry, Mwaba, we'll go right back to the quantization portion of it in a second. I just want to point out other resources and that you could do. Other hacks is like maybe slightly changing the activation functions that you're using. So instead of a tonnage, you could consider using a soft sign or a ReLU. And those are some things that can improve your latency and your memory in case you don't, if you're using like a lookup table to do your tonnage and sigmoid activations. But back to the quantization. So Anani is going to do a quick presentation for us on the shifting that we had mentioned. So yeah, so let's go back to this. Okay.
So yeah, this will basically also show why usually you see for embedded systems, because you get access to that level of optimization. So one of the techniques Maria mentioned can be used to reduce memory or even increase latencies by changing the way you do computation. So in this particular example, let's assume we have just an equation that just needs to be run 1,000 times, that just gives me an output given an X number, multiplies it by a constant and adds a number to it. It's a pretty simple equation, and here are my parameters. So the first approach here is basically to just use floating points. And in low languages like C or C++, you usually have access to that. In higher level languages like JavaScript or even Python, usually it doesn't care the distinction. It just handles all the numbers the same way. But in C, you kind of get that granular detail. So here I just define my parameters as a floating point unit. And then I just run through my operations and I return my result. I'm doing it 1,000 times. You can amplify the differences a little bit better. So we can see the difference here. So by running floating points, that's the cleanest way. It's really the most straightforward way to implement this equation. But if your hardware doesn't have a floating point unit, your compiler will basically take this floating point and try its best to do the computation and give you the result with the hardware that has it available. And the floating point unit processor is basically customized hardware that's been optimized to run floating point operations. And it does that really well. For example, from running this code on my laptop versus the integer operation one, the differences will not be that obvious. But now I'm running it on the microcontroller, the Arduino Nano that we have here that does not have a floating point unit. So the compiler will try its best to convert the floating point units to integer operation and give you the result. In the way it does that, it might not be the most efficient way because it's trying to be as general as possible. So usually in embedded systems, you take the next step. Depending on the latency requirements, you'll now take the next step and just, in this case, I'm just thinking of it as changing the units of my calculation. So here are my parameters. Let me multiply everything by 1,000, do my operation, and just remember at the end of my calculation, I just divide by 1,000 to get back to my original units. So that essentially gives me the actual result in the right unit, but in this case, I'm just using integers to do everything. And so that's one level of optimization. This is also a little bit easier to follow because you just multiply by 1,000, you divide by 1,000 at the end. At a high level, it may look like I'm doing more operations here, but you'll see that the results are quite different. The next level of optimization, Maria mentioned using base 2 operations, and one question had to do about that. At a low level, that's an exciting question because at a low level, the computer does base 2 operations. It only knows on and off. And everything that it does is just some fascinating math around representing your numbers as 0 or 1, and then just doing some operations on just those single bits. So if you take your operation and transform it to the base 2 operation, you're actually getting a level closer to what your computer actually uses to do math. So by doing that, you do actually save a lot of time. So in this particular case, instead of using times 1,000 as my unit, I try to be a little wiser and use times 1,024, which is basically 2 to the power of 10. The only difference here is when I'm done with my multiplication and addition, instead of using the divide by 1,000, I use this operation called bit shifting, which basically says shift my result 10 bits to the right. There's some low-level hardware stuff that if you look deeply into that, it actually makes sense why this is actually faster than actually doing the division operation. And the next one, let me show you the results actually. So here you can see with the floating point operation, it's taking me 255 milliseconds to give me the result here. But by going with base 10, integers only, I'm going lowering it to 150, which is drastically faster than if I was just doing floating points. I'm just increasing the complexity a little bit because now I'm dividing instead of just doing multiplication addition. And then when I go to base 10, the difference is even more drastic. I'm just to 100. But this is where the cost starts to come. Because I'm using 10 bits, now I'm losing in my precision. So the result is close, but because of the roundings that I'm doing here, for example, here I'm rounding my 289.7 to 290 and the other one there too. So I'm losing a little bit in precision. So the way you usually address that is just increase your bit shifting. Instead of multiplying by 1,024, let's go overboard and use 2 to the power of 16, which is 65,000. And I basically multiply my constants, and these are what I'm rounding here. And at the end of my addition multiplication, I just shift by 16 to bring it back to the right units. And in the results here, you can see the time is exactly the same as the 10 bits, and I'm getting the precision that I need. So looking at that, this is how you can really drastically improve performance by just getting closer and closer to the language that your computer speaks. And at the bottom of it, it's really just handling on and off base 2 operations. Any questions on this? So yeah, I hope that answers the base 2 question there, because a lot of times that's really getting as close as possible to what your computer can use. And this is where C helps. And even if you go level lower, assembly actually takes you a lot closer to what your computer does, but by accessing register directly and just doing some fascinating math on the numbers.
Okay. All right. So for the last portion, we're going to use Edge Impulse to train a model. So if you don't have a board, that's fine. you can use your phone or your laptop to collect data. So this is a project that you should feel free to clone, but you don't have to. You can also just log into your Edge Impulse account. I don't know if everyone has an Edge Impulse account just yet, but that's the link. You can sign up. So I can share my screen now. Can everyone see my screen? Okay. All right, so you can log in. I already have an account, but if you don't, you can just sign up and set up one account for yourself. So now you can just sign up there, set up an account. So I'll go to this project that I just shared, and you can just hit clone this project if you want to use this one. If not, you can create your own new project. So when you open it up and you click create new project, you can name it DSA 1, and that will create a project for you. Okay. So we can start by, I don't know how many people have their boards connected or not. So if you have, let's select audio for our project. And if you have a board, please connect your board that you have. If not, that's fine too. We can use our phones.
It's different from the number. They have the number that doesn't have sensors.
Oh, that's true. That's true. Oh, yeah. Sorry. Yeah. So if you probably don't have sensors on yours, so we can just use phones to collect data. But yeah, so. If you go to devices and you say connect a new device, you can use your mobile phone to connect your device to it. So it will bring up a QR code. I don't know if you guys can see my screen, but it will bring up a QR code and then you can just scan it using your phone and open it. And then we'll connect. So, okay. So once you have your phone connected, you can do some data acquisition. So, okay. Yeah. So ideally you want to collect, so here we're going to train a keyword spotting algorithm that can detect the words on or off. And so you'd want to collect sound of you saying on and sound of you saying off multiple times. More data is always good.
Do we need to clone the project?
Oh yeah, yeah. You can clone the project, but you also it's not like a must. You can also make your own project if you just want to start from scratch. The project that you'd be cloning has already been designed, so it has like a preliminary design and like 1 minute of data that you could use. So that's the only difference. But I used my project was the data was collected using the Arduino Nano 33 BLE sense board. So if you want to use your phone to run this project, the data would be slightly different. Yeah. I don't know how, like, if people are like, at this level, but I guess I'll just do like a quick run through of how everything works. And then we can just like, I guess, do breakout rooms or something and just try to develop a tiny ML project. Does that sound good? Yeah, no, okay. All right, anyway, so once you have your phone connected, it should bring up a screen. And so, I don't know but if you can see my phone, it should bring up a screen that says, oh yeah, if you're using a computer, you can, yeah, just select use your computer. If you don't have a phone, yeah, you can just use your computer. I guess that would be easier because,
if you're only using a microphone.
yeah. Okay, so we can do use your computer. So I'll just go back to devices and then connect device. You can use your computer to collect data. So it should bring up a page like this, and then you can collect your audio, right? So give access to the microphone. You can collect your off data initially, set your length to how long you want it to be, and then you can do a split, and then you could just start recording. Off, off, off,
Off,
off, off, off,
off,
off, off, off, and
off.
off.
I'm just trying to make it work, this job harder by adding different types of voices.
Exactly. So that's like a quick way of like collecting data. And if you go to the data acquisition, you can see, ooh, sorry, I was muted. So I didn't actually record. I'll just delete this. Myself and then do it again. Off, 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 off,
Off.
off. And so this is what your data should look like. So it has points where you're saying off, right? I don't know if you guys have used Edge Impulse before and you know how to do this. But then you can then split your sample so you can extract the sections that say off, and you can just kind of adjust this to where you want it. So this algorithm does a great job of kind of isolating your off segments. And then just split those. Okay, and then you can do the same thing for on. Collect the same data here and use on instead of off as your label now. So you just change this to on and then collect some data. You can use any keywords that you want. Actually, you don't have to use off or on. You can use your names or something else. And so you'd collect your data here, lots of data, and then you'd create your impulse. So your impulse is basically how you want to design it. Here I'm using a window of 1000 milliseconds, and this determines your overlap. So you can, overlap is good, so you can change that if you want. Yeah.
There's a question on mobile connection. How to collect the data.
Oh yeah, so the QR code will just show up on your phone. So if you go to connect device up here, connect a new device, and you use your mobile phone, it will show you a QR code. So you just do, the QR code pops up on the website. I don't know if you can see that. And you just need to scan the QR code using your phone. So using the camera on your phone, just scan the QR code. That makes sense. So just, yeah. So you guys can all collect, yeah, so you guys can all collect data in here. So you can collect up data, on data, and then some noise as well. So you'll have different categories, and then you can create your impulse. So this is your time series sample. You can add a processing block, and this is just kind of your feature extraction or signal processing that you'd need for voice data. I guess, yeah, EduPulse has this cute, nice hints. So you can just add this block, and then you could add Facebook. Are you connected to the internet? Lava.
I think, so yeah, now it depends because it scans, there's a link that the QR code has that opens in your browser.
Yeah.
So it depends on your camera app itself.
Okay.
Yeah, so if you have a QR code reader, you can scan and copy the link from it and paste it in your browser.
Is that when you scan it, Stanley? Is everyone able to use their phone? I mean, their laptops to do settings here?
Yeah, I feel the laptop may be the easiest approach for this afternoon.
Okay, good. All right.
So if your phone is not working, you can try your laptop instead. In this example, we're only using audio instead of on-C sensors that your phone may have.
Yeah. Okay. So yeah, I'll just I'm gonna go over everything here, and then we can go into debugging. So yeah, so you can add a processing block here, and then you can add a learning block. There's like a few defaults that you have from Edge Impulse. So I'll just do a classification. Right now I only have one feature, but when you collect more, you'd have like off and on and different things actually. So in this, here I created my audio with an MFE, used a neural network, and had 3 features in there. So that's kind of how you do it. And then you train your network, right? So you train your network, your neural network here, and it would learn. You'd set the training cycles, learning rate. You can change your architecture as well over here, and then just train it. Mine was really simple. I had little data as well. So there's a possibility it's overfitting. and it was just my voice. So you need to collect more data. So to see how this would work, but this is just an example. And then Edge Impulse has this thing called the Eontina, which is kind of cool that you can run, and it just goes through different designs for you and figures out which one is optimized for like speed. So down here you can sort based off accuracy, your latency, your RAM, and your ROM. So you can choose the best model for whichever thing you're trying to optimize for. So this is kind of cool. You can use that. And then once you have that, you can retrain your model as well. And then you can do live classification. So you can classify it in your test set as well. And then this is when I've classified it in my test set, I got about 97% accuracy. But again, I had a few samples and it was just my voice. One sample was classified wrong in my particular situation. You can save a version of your model and then deploy it. So now we don't, I think most people don't have the hardware. So you can just save it as an Arduino library or as a C library and deploy it to your device later on. But if you have any of these firmwares, you can just create binary file that uploads directly. So that's just kind of an overview of how to use Edge Impulse. And so I guess now everyone can just start like, collecting data if you're able to access it and creating your own networks, Edge Impulse networks, and your keyword spotting algorithms. That makes sense. All right, so see. On, 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 on,
On.
on, on. Here.
It's my voice there.
Which one is it?
My timing is off always. Yeah, it's fine.
Okay. Add a segment.
So folks are able to connect the phones.
Okay.
There's a question on how do you collect the information
How do you collect the information?
once you've connected your phone?
Oh, once you've connected your phone, you can, so once you scan your the QR code, your phone should bring up a menu and you can just hit collect audio. So I'll show you in a second. So this is what you should see. Can you see it?
So yeah, you should have 3 buttons with
Yeah.
the option to start collecting.
Yeah, so one of them says collect audio. So you should just be able to select collect audio and then record yourself. Yeah, so this is one way that you can build your models using Edge Impulse. If you're able to get access to hardware, you can deploy these models and do live testing. I don't know how many people have access to it, but you can do that. Hardware that has like the microphones and the accelerometers. Yeah. So yeah, so you can do that. So I will connect the board to my machine and show you a demo. Okay.
So also in the meantime, if people have some questions, feel free to post them so we can go over them before the end of the time after the demo. Have people used other wake words as the recording? It's funny ones.
Is it sweet? Okay. So when you're building a model, say you have like a model that works well and you want to deploy it to your device. In this situation, in this case, I'm going to build firmware for the Arduino Nano 33BLE. So you just select that and then make sure your performance is what you want. Your RAM usage is good, your latency is as expected, you have good accuracy, and then you just select build model. So right now, Edge Impulse is building my model, and then I'll be able to deploy it to the hardware that I have in just a second. And you'll be able to see that.
How does it perform non-binary classification?
So Edge Impulse has access to regression as well. So you can do a regression task if that's, I guess, kind of, if you're not doing, I guess, classification. If it's more than one class, so in this case, I have 3 classes, noise, off and on, and it will just make 3 it will have 3 outputs as your classifier and do a probability of that using a softmax function. So you can have as many classes as you want, and just make sure, yeah, and then design your network based off of how well your performance will be. And this Tuna would help you as well, just kind of like do like a quick search to see what model design works best for you. I don't know if that answers the question.
Any limits on number of classes?
I would say like I'm actually not sure if there's a limit on the number of classes in this hardware particularly, but I would say that when you're designing your tiny ML model, this would be based off of like how I guess distinct you want your classes to be and how big they want to be, right? So if you have like say 50 classes, that may be like a bit too much, and I don't think you'd want to output like that many outputs in your algorithms, slash it would be hard to train one. But I think I've seen cases that have like 4 or 5 classes. I'm actually not sure if there's a limit. That's a good question. I could check. Um, So let's see, there's a question about,
Creation process.
okay, oh, the creation of an impulse. Yeah, so for the impulse, you would, based off of what data you're using time series data, you could set your window size. So this is just like, what size of window do you want to classify? So what, how many seconds are you going to, of data are you going to collect? And then classify on that. So in this case, we selected 1000 milliseconds. This window increase can determine your overlap. So you can adjust it to give you more or less overlap. In this case, we have 50% overlap, so we can set it to 500 milliseconds. You could go lower to 300 milliseconds as well. And then here you could create your processing block. If you add a processing block, this is just like your spectrograms or any feature extraction you can do on your data. So for time series data or audio data, you can use your mel frequency, substrate coefficients or spectrogram, and you can try different ones or add multiple to your design. And this is where you do that in this processing block. So it's like pre-processing. And then you could add a learning block. So here you'd add a learning block. You could do a classification task if that's what you're doing. And this will create the default classification neural network here. And I'll show you in a second where you can adjust that and write your own code. So that's where you do this neural network design part, and then you'd have your output features here. So I have noise off and on, and you could have different wake ones or different things that you want to identify, classes that you want to make, and you'd save your impulse. And once you do that, it would create your audio block here where you can change your results. So because I use the Eon tuner, it created these results for me automatically, but usually it will bring up different things that you can optimize for in your design. And then in your neural network as well, it will show you like the layers. I have 1D conv nets, so you have your different convolutional neural networks, you have your dropout, and it will give you your classes, you set your epochs and your learning rate, and you can train that. You could start the training, and it's outputting 3 features here because I have 3 classes. And then this is the thing I was talking about. So that's how you create your impulse. And then this is the one that does kind of like the search algorithm for you. Okay, so my binary file downloaded. And so you can extract it.
What inputs or signals can impulse use?
What input signals?
Yeah,
Oh.
sensors.
Oh yeah, so I will show you that in just a second. Okay. So here, I think there's like where you can, it shows you. Okay, so in the beginning, when you like open up your algorithm, there's different data files that it shows you that you can acquire. So you can do audio, you can do your accelerometer. So now I don't have anything connected, but you can change based on the sensors you have. So let me see if I can start a new project and we'll show you that. So here, so you can do your accelerometer data, you can do your audio data. This says images. And then if you have a sensor that's on your device, but is not supported on Edge Impulse, you can just collect the data on your own and then upload the data to EdgeImpulse as well, based off of whatever sensor you have. So if you have like a humidity sensor or a temperature sensor, you can just do that. Yeah. Yeah, yes, correct. Okay, so here, so when you're done building your file and you download to your computer and you have your board connected, you can just extract these files, mine extracted here, and then just run this binary file. So I run it when I was explaining this, and it gave me, it like downloaded to the board that I have connected here. Close this, and then when you open up, oh, you only see the browser. Oh, okay. Sorry about that. Okay, so do you see everything now? Okay, so now you can just do. Okay, so now it's doing inferencing and it's detecting lots of noise with a high probability. My classes might also be heavily tilted towards noise, but I'm going to try saying off, off. This is so weird. Yeah, so. Yeah. Okay. Clone a previous model. So if you have a previous model, you can just make it public, and then people will be able to clone that, and then you can just it will show up on your website, and you can just, show up as a link that you can just click to clone, if that makes sense. Yeah. So let me show you how to do that. Here, you'd make the project public, and then people would have access to that. Yeah. Okay, so yeah, so my impulse, the data that I collected had more noise and more on or off data. It was about 1 millisecond. So you want to collect about 1 minute. So you want to collect about 10 minutes of each class that you have and run this training. Right now you can't deploy it because you don't have boards, but in the future when you do, you can try this. And in the meantime, you can collect data using your phones. One thing to note though is that if you're going to deploy this device on an actual embedded system, you might want to collect data with a system on which you're going to deploy your algorithm. So that will reduce issues with like data drift or differences in the data, and will help your algorithm to learn much better to kind of the data that you'd expect to collect in the field. You also want to collect noise or like abnormal data, so it can be able to detect that, if that makes sense. But yeah. Yeah.
Yeah, that's critical because your phone will already be doing some additional processing on the raw data that
Yeah.
your embedded system might not be doing. So given at that point, your inputs are pretty much different. You'd have to do the same processing that your phone is doing if you collected it by your phone or that your computer is doing.
Yeah.
You disconnect your PC after collection. I think closing the window should stop it.
Yeah.
Yeah, closing the window should
Just close,
the
yeah,
tab.
just close the window, so.
Yes, we have 10 more minutes.
Yeah, and EdgeImpulse has like lots of resources that you can take a look at later when you have access to some hardware. They have a bunch of resources and people are using EdgeImpulse now. I guess a few notes for TinyML I would say is like it does help with IoT data processing. There might be a way to use both of them in a system as opposed to just switching completely to TinyML or mainly using IoT. So there's like a good balance between using TinyML and IoT to solve your tasks. That's one thing to note. Yeah. And yeah. So, yeah.
Parting words. So yeah, in general, thank you for the time. For embedded systems, it's one of those fields that it seemed daunting at the beginning, seemed to have a pretty steep learning curve. But nowadays, with all the dev kits and resources available online, you do have a lot of resources to help you navigate through that. We'll make sure to include a few of those examples in the presentation that we'll share. And available as resources if you have any questions. Find us on LinkedIn, ask a question, anything like that.
Yeah, and for the board that you're asking that I selected, that was the Arduino Nano 33 BLE Sense. And that's because that's the board I'm using right now that I have connected to my PC. So the board you'd select would be dependent on what you have, what hardware you have. If you have none of the ones available, you could just create a C library or an Arduino library and then run it on the board that you have. So yeah. To answer your question. I did not select anything on that. I just built the firmware directly. With the Arduino Nano 33 BLE. Welcome. All right, we'll let you guys.
It's challenging, but what you can do is really, I personally like being able to write software that interacts, links a real world LED or changes something physically. So it's really satisfying when you get it to work in the real world instead of just printing messages on the console or something like that. But yeah, like we said, there's a lot of resources available nowadays. A lot of times it was really the hardware needed to get started that was the gate stopper, but with platforms like Arduino or Raspberry Pi, there's a lot of way you can get started with this. Yeah, that's a good question. Yeah, I would say getting something like an Arduino. The beauty of Arduino is that they do provide a lot of help and examples. You will eventually have to learn C or solidify your language in C. But by using Arduino, they'll basically walk you through. On the website itself, they actually have full detailed tutorials going through each examples and how to move from one system to the other. So getting an Arduino with the required peripherals will really help start the journey to embedded systems. And then with that in place, you can now put your knowledge of machine learning to the TinyML and tools that Maria demoed. And the sky's the limit once you have that. What's the difference between Raspberry Pi and, so yeah, those are different, that they use different processors and different abstraction levels for how you program it and what you can do with them. The Raspberry Pi is a little bit more powerful than the Arduino, so you can do a lot more of it. The Arduino is really meant for really tiny microcontrollers with some peripherals, and Raspberry Pi, you can run, there's some Pis where you can even run Python code directly on it. But all of them are hardware platforms to get you started in your journey to embedded design and applications. Sounds good. We'll make sure to provide the resources.
Okay, maybe I can just jump in and say that thanks a lot, by the way, for the session. It's been really great. So the plan was always to get at least some resources to a few places within Africa. Of course, we couldn't get it to everyone. So what we're trying to do is maybe we have a few hubs. So we are starting off with Kenya, Tanzania, Uganda, Zambia, and South Africa. And we have sent out a few kits, so of the order 10 to each of those, or I think maybe 5 to some places. But the idea is, if your interest has been piqued by this session, we'll let you know how you can get this hardware. So I mean we'll email it out, and we can explore this a little bit more. And in addition to that, together with Maria and Anani, I think we'll be look out for a series on TinyML and IoT, a more in-depth and essentially a dedicated DSA TinyML series. So be on the lookout for that.
Okay, sounds good. Yeah, thank you for having us. This was really amazing.
Yeah, thank you.
Awesome.
Okay.
Okay, sorry, I didn't mean to bring an end to things. We still have quite some time, I think 3 minutes for more questions, but I don't know whether you'll be available in the afternoon, or I know we'll be asking a lot from you, but if you're available, there's also a slot for more one-on-one interaction with the participants.
Okay, yeah, sounds good. I think depending on the timing, we'll get some sleep and wake up and see if we wake up in time. But we do remain available. People can find us on LinkedIn. We'll keep in touch with you, and I'll provide the details for all the material we've covered and starting tutorials and all that stuff.
Great, thanks a lot.
Awesome. Yeah, definitely. Thank you for having me.
Okay, thank you so much, Mr. Anani and Ms. Maria. And can everyone please give them another round of applause for such a fantastic session?
Thank you, thank you. I imagine with if the audio was on. Oh, I see the clap. Perfect. Thank you.
Yeah, and I must say, initially when I heard Ms. Maria was she saying on? I was wondering what was happening, and then afterwards I realized that she was collecting data.
Yeah. Sorry about that. Yeah, I should have mentioned that. I was trying to collect data using my laptop and my phone as well.
No, it was quite interesting. Thank you. And I don't know if there's any final comments from the attendees before we move on to our break. Okay, I see there's a question. Someone asked where can they connect with you guys. I don't know if you're going to leave your LinkedIn details as you mentioned earlier on.
Yeah.
Yeah, thank you. I will add those to the presentation slides that we'll submit. All the details there.
Okay, thank you so much. Thank you. And with that being said, we are going to then move on to our break session where just everyone can go and stretch their legs, get some coffee, some tea, maybe have breakfast if they woke up really early and didn't get a chance to have breakfast.
Awesome. All right, thank you. We are signing off.
Okay.
And for those of you that are just still here and not going anywhere, I just wanted to find out if one or two people are brave enough to just comment, just unmute themselves and just say where you're from. Okay, I'll go first. I'm from South Africa, and maybe if you can also add on and say what you're currently doing, if either you're studying or you are working.
Hello, everyone. I'm Gabriel from Kenya. So I'll be presenting during the next session. And there was some request for you to set up our repository and the environment. So there have been some changes. So I would request if you are available now to pull the current changes in the report. So I guess you all received an email telling you giving the instructions. So kindly pull the changes for the next session.
Pardon me, sir, you are not very audible. Can you please repeat what you just said?
Hello. Can you hear me
yes,
now?
Sir. Yes, sir.
My name is Gabriel from Kenya. So we'll be presenting during the next session. So there was some instruction that was sent out to your emails telling you to set up our report and create the environment. So there have been some changes in the repository. So I would request those who are here to pull the request, to pull the changes. Okay, let me type the
Yes, sir. Could you please perhaps type the instructions? While we wait on Mr. Gabriel to give out the instructions for the following session that's about to take place, can if people can perhaps comment in the comment section if you don't want to either raise your hand or just say something. Maybe perhaps just say something interesting about yourself or about your country, that if someone were to go in and visit there, then they should maybe go and see that place or try that specific food that is peculiar to that place. Can maybe, because I saw in the comment section that someone said that even though they don't have much of an idea of what data science is, they still found it interesting. Can you perhaps comment out if you have any idea of what data science is or not? And if not, how has your knowledge changed ever since you started attending the summer school since yesterday? So the repo for the next session has just been dropped. The link for it has been dropped in the chat section. So that's the current one that we'll be using for the session that's going to take place. Okay, so how far are you guys with the hackathon thingy, the hackathon competition that we had received yesterday? Has any of you started with it? How's the progress going? Thank you so much for that comment. Even though you didn't really get anything from yesterday's sessions, the recordings are still there on YouTube. So if you have time, maybe after this, you can just go back and watch everything. It was quite insightful. I'm sure you'll get one or two things after watching that.
May I ask how many people are members of our DSA mailing list? There's a vote feature here on Zoom, but maybe you can just tell us on the chat if you're a member of our mailing list. We often post quite some information there or on our Twitter handle, and yeah, and mainly those two channels. So if you'd like to be
Sorry, so someone asked how do they join the mailing list?
So I'll be able to maybe the best approach would be to add the registered participants, and those who would like to join would then sign on. How does that sound? Good.
There's around about 3 minutes left before we start with our next session. I think if all the presenters are ready, we can just jump in and start with it. There's just like 2 minutes left. Is that okay?
Yeah, we can set up and then just wait to start on time, and then take it from there. But I can set up we'll set up in the meantime.
Okay, sir. So in the meantime, before we start, maybe people can just comment on and say how they heard about this data science school. Maybe it was like a friend or saw it on the website or somewhere. So the Internet of Things has been described as a network of interconnected devices which communicate with one another through network protocols. So then let's see how this is applied in data processing. So let's give up for Mr. Kyra, Mr. Jason, Ms. Lana, and Mr. Gabriel, who are from the Dayton Kimati University of Technology and from the Center of Data Science and AI. So let's give it up for them, guys. Let's give them a round of applause.
Okay, thank you. Thank you very much for the introduction. And we're very happy to be able to present here. Maybe I can just, I hope I'm clearly audible.
Yes, sir, you're audible.
Oh, great. So my name is Shira. So I'm also, we met yesterday as part of the organizing team of Data Science Africa. But in addition to that, I teach electrical engineering at Dedan Kimathi, that's in Nyeri, Kenya. And today, together with other members of the DSA lab, which is the Center for Data Science and Artificial Intelligence at Kimathi, we'll be looking at IoT data processing. So it'll be hopefully quite hands-on. And so I'll be joined by Lorna, Jason, and Gabriel. I should also mention that DSAIL is also supported by DSA as an affiliated center. So we are part of the and parcel of the DSA community. So IoT, I'm sure it's quite a buzzword nowadays, you know, interconnected sensor devices, collecting data, interacting with the environment. The previous session was an introduction to how you can actually write code that that can actually go a long way in interacting with the environment. So we do a lot of coding with microprocessors in order to be able to collect data. And this allows us to measure variables of interest all over. So for example, Anani was giving an example of collecting data from a volcano, like if you're monitoring seismic activity, or doing applications in health. A lot of people wear wearables, especially to monitor things like activity, you know, exercise and things of that nature. There's a lot of work in monitoring the weather. And a lot of that is now moving to the realm of IoT, where these devices, while they're deployed out there in the world, they're collecting data and sending it to be processed or processing it actually on the edge. And that's where TinyML comes in. So at DSAIL, we've been developing a few systems that do this data collection and data processing. And we want to take you through a few examples. And in particular, we'll be looking at the area of anomaly detection in time series data. So Jason will handle that and will explain what all that is about. We'll look at acoustic data. So you had a keyword spotting example in the last session. We'll go a bit in depth into how those sort of applications are built. And if we're able, we'll look at some image processing applications using camera trap data. So all these are real world deployments that have been developed at DSAIL and actually are out there in the real world. So for example, there are applications that are monitoring water level in rivers near our university. And the sensor data that is collected there ends up needing to be processed before you can do any insights. And one of the first things we do is anomaly detection. Jason will explain what that is. We have other examples of collecting acoustic data to do processing. So we have systems based on the Raspberry Pi. You were introduced to that in the last session. So these are this microprocessor and small, almost computer system on as a standalone computer, really. That's what a Raspberry Pi is. But we're able to design it in such a way that we can deploy it out there to collect acoustic data. And what you then do with the acoustic data is things like acoustic ecosystem monitoring. In other words, we are measuring how well the ecosystem is, and that will be explained by Gabriel a little bit more. There was a notebook we designed for a problem after talking with our colleagues at SPU about monitoring road traffic using acoustic sensors. So that is something that's possible. And we'll explain a little bit of that. And the last part, which we'll try and get to, we'll be looking at the processing of camera trap images. And camera traps are used in conservation areas to monitor wildlife. So the image we have here on the left is a camera trap that has been deployed at our university's conservancy. And the sort of images we get from it are like this on the right. These are some impalas. And I should mention that our university is located in a very pristine ecosystem, I would say. And in fact, these impalas are probably, I could take 10 minutes to get to them. And that makes our lab quite interesting. I mean, we're able to do this sort of work in conservation. So without too much ado, this is a plan, and I'll hand over to Jason so that he can take us through the design of his system and the processing of that time series data. So over to you, Jason.
Okay, Doc, can you hear me?
Yes, I can hear you.
Okay, thank you. So, hello everyone. My name is Jason. If I turn on the camera for everyone to see, my name is Jason from Center for Data Science and Artificial Intelligence at Dedan Kimathi University. And I'll be taking you through anomaly detection in water resource monitoring and catchment analysis, basically water level data. Let me share my screen here for a minute. Okay, so basically my topic today will be on water resource monitoring and catchment analysis. And a little bit of a breakdown. I'll be talking about the motivation behind the whole project, the main goal of the project, what water parameters are being monitored, and how are we monitoring the parameters, the hardware development for monitoring the seed parameters, data acquisition, and data analysis. Our main part will be on anomaly detection. So diving into it, so the main goal here is river catchment analysis using water level data by leveraging IoT and machine learning. So the takeaways here are that water level data can be used to diagnose the river catchment by watching the water level trends over some time. So the image here on the right, you can see that we have a bare land and you have some land with vegetation. So when there is a lot of rainfall, the amount of runoff on the bare land will be a lot compared to where the land is a little bit pristine and we have some vegetation on it. So we expect when the catchment is bare, the water level in the river should rise very sharply and quickly as compared to when the land is covered with vegetation. And with that, you can use that understanding to diagnose the catchment, whether it is highly degraded or it is pristine, it is conserved. So water level data can be used to make that qualitative analysis in that how long does a spike in water level take to occur after a spike in level, because like I said, you observe when the land is bare, the water level rises sharply compared to when the land is covered with vegetation. And other data sets can come in also into play, like water turbidity, because when the land is bare, you expect the turbidity of the water, in that the cloudiness of the water to be high. So you can collect that data using turbidity sensors. Also, the water flow rate can be another useful data set in this case. So moving on, our catchment under study is the Moringato watershed. These are watershed in Nyeri County in Kenya. It is very big, but compared to the whole country, it is quite small. So it is at central Kenya here. I'll be going through it on a well-defined map, but this will have to do for now, in that on the left here, you have the images where you have the forest. It is a highly forested area. Then as you move out of the forest, you have the settlements and you have the farmlands marked by the gray and the red patches. So the river we are monitoring, the water level in, runs from the forest here out to the farmlands and the settlement areas. So basically the watershed becomes a very nice specimen for the study. So like I say, you have the river itself here. It has quite some small tributary, but this is the main stretch, as you can see. So we have the forested area, then out to the farmlands and the settlements. The red dots here marks the deployment of our water level sensors, which collect the water level at different intervals. Some collect at 5 minutes, other collect at water level intervals of 30 minutes. So we have them lined up. Then we have the red star there marks the position of our gateway. That's the roller gateway. We are using the roller 1 network, which is an IoT network to transmit the data from the sensor nodes to a cloud platform here, then to the database on the cloud to store the data. So basically the layout is a very simple layout in that we have the water level, then you have the devices that collect the water level. So basically you have a microcontroller, an ultrasonic sensor. Then we have the roller network and the gateway. We have the IoT network server. That's the things network. We are able to register our devices and see the data that is streaming in. So from there, you transmit the data to a GCP cloud storage. That is an influx database. That is a time series database on the cloud, on the Google Cloud. Then from there, you have to anomaly detection. That is what we will be talking about to get rid of the anomalies in the data set. Then from there, you can visualize. I'll take you through that also. Also, you can do some further machine learning using the data, like prediction models or other algorithms for anomaly detection in this case. So basically here, we have the main microcontroller here is a multi-tech M dot, or you can use an Arduino with a roller transceiver. So this is just a matter of choice. So the device here, we have various types of devices. You have the one that uses the multi-tech M dot, which is a very reliable piece, microcontroller piece. Then we have such kind that uses the Arduino Nano, the one Maria and then we are talking about. You have the Arduino Nano connected to a roller transceiver here, the green piece. Then you have an edge antenna socket. You have the battery, a lithium-ion battery that provides the power to the whole system. You have the ultrasonic sensor. You have the boost module, some power modules here to handle the distribution of power over the board. So basically, this is a PCB, an etched copper board that we use to facilitate our deployments. And you can see a system that is deployed. I deployed this, I think, back in February. It has been running throughout the year. And I'll be taking you through the data it has been collecting. It has a solar panel and now the main device that is collecting the data. So up next, we'll be talking about the anomaly detection on time series, the water level data that I've been collecting. I'll take a piece of the data and we'll be going through it and detecting anomalies using some clustering methods. So let's jump into that. Let me stop the sharing here and maybe share my notebook. Okay. Hope it's visible. So we start with anomaly detection here. So basically, we are going to use some clustering algorithm, basically K-means, which is a clustering algorithm to detect anomalies in the water level data collected. So what are anomalies in IoT data? So basically, this is unexpected sensor readings that you may expect from such kind of the devices that I was showing you some minutes earlier. So, and these anomalies are brought about by maybe exposure to harsh environmental conditions, and also vandalism, breakage, and all that kind of stuff. So sensor prototypes that are deployed in potentially harsh weather conditions for tasks like environmental focusing. So, I failed to mention, if you have to fire this notebook, fire up the notebook using the instructions that were provided yesterday. If you have not fired up the notebook, maybe I can provide a link to the Google Colab and you can use that. Let me just share this link with you.
Maybe we can pause and ask if people have been able to fire it up.
Yeah.
To start the notebook.
So that's basically the link to the Colab notebook. If you have not been able to fire up the notebook on your computer, you can use the link to the Colab. And also, you can give me a notification if you have been able to fire it up on your, or fire it up locally on your PC, so that we can move together. So you have the link on our GitHub repo, you have the link to the notebook here. And on how to load the data set, you have some instructions below there, very simple instructions on how to load the data you'll be using today. So basically, yeah, these are the instructions. Okay, let's go back to the notebook. Like I was saying, that prototypes deployed under harsh weather conditions for tasks like environmental monitoring, just like what we are doing for the water level. They are prone to breakage and damage, and also so you have anomalies appearing in your data set, the collected data set. And for anomaly detection now is a process that is very important in the processing of this data. So you get rid of these anomalies and you have a very clean data set. And today we'll be looking into clustering as a method of anomaly detection. So clustering is basically an unsupervised machine learning technique that is used to understand the structure of a certain data set. So basically unsupervised because the data set is not labeled. You don't have labels on the data set. So you can use the clustering method to just get an understanding or an intuition about the data set that you have. So basically you identify subgroups in your data set and you are able to group the data set, the data points that you have into clusters. So the catch here is that the data points in the same cluster are very similar, but the data points in different clusters are very different. So you have very similar data points clustered into one cluster. You have some other data points are clustered into another. So the data points in one cluster are very similar. So basically that's the catch. So and then in application, you can use clustering algorithms on scikit-learn like k-means to cluster the data basically. And the assumption is that the cluster with a few data points in anomaly detection are the anomalous clusters. in that those clusters that you find when you are done with the clustering job is that those clusters that have the few data points are the anomalous clusters, and they will take you through that. And the main cluster end up being the cluster with the correct data points. I take you through that too. So basically, this image shows you that you have the data before clustering. Yes, you can get some understanding of the data, but using a clustering algorithm like k-means, you're able to cluster the data into different groups. So basically, what's k-means? K-means is basically an unsupervised machine learning technique used to identify clusters of data objects in a data set. So basically, you are able to cluster data points. It might be two-dimensional in that you have a varying x and a varying y, or a random x and a random y. Or it can be a one-dimensional where you have a deterministic x and a random y. I'll be talking about that. So you have a deterministic x, you have a random y, like our example that we'll be using. So it is a very simple technique to use. K-means is very simple algorithm to use, and it is also very approachable. So the steps followed in K-means is that you specify, by looking at the data, you can specify the number of clusters that you want for your data set, the clusters K. Then you initialize centroids for these clusters by first shuffling through the data. And then after you initialize the clusters, we iterate until there is no change. There is no change in the cluster, in the centroid. No change to the centroids. Then you compute the sum of the square distance for all data points from the centroids. And now with that distance, you can be able to cluster each data point you can able to attach, if I may say, each data point to each centroid here. So moving on. So the main point here is that you have to iterate until there is no change in the centroid. So basically, if I may take you through an example, in that where if we are able to run this first set here, when we are able to generate just a sample data set using two Gaussian mixtures here. In that, if you run the first set here, you can see that you have two clusters by just looking at the data set. So we intend to cluster these using the k-means. So for that, so here we imported the NumPy to help us with that, the matplotlib to help us with the plotting. We went through that yesterday, pandas to help us with the data frames, and also the scikit-learn. We import the algorithm k-means for our clustering. So by running the second set here, you can see that our data set is clustered into two. In that, you initialize the number of clusters you want. You have two. In other points, I'll take you through an algorithm where you can actually use another algorithm like the elbow method or the silhouette score on scikit-learn to help you decide on the number of clusters you may want to use for your data set. So you can actually see that we have clustered our data into two clusters. The yellow dots here represent the center of our clusters. Those are the centroids. First of all, these yellow dots are initialized as random points. Then they are iterated until there is no change in them. So then these data points are attached to this cluster, to these centers. So you can see that if we extract our data points labels here, you can see that we have the labels for one cluster, which is basically a 1. Then you have labels for another cluster, which are basically a 0. So that is to tell you that we have two clusters in our data set, basically depending on the color of the on the labels, and you can leverage this property to give these clusters that are a different color from the other, and that is what I have done here. As you can see in the code here, I've leveraged the labels property here to give the clusters the color. Then let us predict the cluster for three specific data points, or these three random data points. Like you can have a data point 0.5 by 0.5. Then you have a data point 3.2 by 3.2, another one 0.8 by 0.8. So if you run this cell, you can see that the first data point is clustered to the cluster with the label 0. So with this cluster, so then the first data point here 0.5, and that is what you expect, in that you have 0.5 here by 0.5. So this is the cluster. The second one, which is 3.2 by 3.2, 3.2 by 3.2. So that's our second cluster, is given a label 1. Then you have 0.8 by 0.8. So 0.8 by 0.8. So this is the cluster here. So basically that. So you can actually predict the cluster for certain data points by running that. So let's introduce our data set for today. And the breakdown here will be.
Jason, there is a question.
Okay, oh, sorry. Oh,
there's a question in the chat.
Okay. Should we have the same color for each set of points? So, okay, so if I may understand your question, in that you just to differentiate between the clusters, you have to have different colors for a specific color for each cluster, so that you can differentiate between the two clusters, if I get your question. So you have the red to signify that that is one cluster, and you can actually see the labels for that cluster, the 0 label. Then you have the purple to signify the other cluster, which is the cluster with the 1s. The label is the 1. Then the yellow points here are the center for those clusters, the two centers for those clusters here. And you can see actually see the coordinates up here. Oh, sorry. I can see that for me, the red points are the colors are random, are assigned randomly. So if the clusters change the color, there is no problem in that. Just the colors are just to signify different clusters. Okay, thank you for your question. So moving on. So using K-means to detect anomaly in the IoT sensor. This is the river water level data I've been collecting. So using my prototypes that I showed you a while earlier. So we are going to import the data. This is I prepared a sample for this demo. Then we'll go through it. So let's import the necessary packages there, just to visualize the data. And you can run the second cell. And you can see that actually there are very random anomalies. They are quite periodic. This is due maybe to a shake of the prototype, that the prototype was shaken. So you can see that they are quite periodic, and we'll be using K-means to get rid of these anomalies and retain this trend at the bottom here, above 0.25. So like I said, you can do clustering for 2 dimension, in that where your X and Y are random, or you can do it for 1 dimension where your Y is random, but your X is deterministic, in that you are like this time, like in this case, these data points were being collected at 5 minutes intervals. So I coded up my system to collect the data points at a 5 minutes interval. So that is a predetermined value. So you'll not be using the X-axis, the time axis in this case, but we'll be using the Y-axis. So this clustering is 1 dimension. So let's now decide the number of clusters that we want for our data set. We have just visualized it. You have the anomalies here. Then you have the main trend across across the graph, running across the graph. That is where our main cluster. So deciding on the number of clusters you may want for such kind of a data set, because with this, you cannot just look at the data set and say that I want maybe 4 clusters, 3 clusters, because there are a lot of data points. So you need some algorithm to decide that for you. So you can use, basically in Python, there is something called the silhouette score. That's an algorithm that can be used to decide on the number of clusters you may want for your data. Or maybe there's another algorithm like the elbow method that can also be used to decide the number of clusters you may want for your data. So the silhouette score is basically used to determine the optimal number of clusters by determining the degree of separation between clusters. So for each data point, alpha, for each data point in your, if I may run through this with you, for each data point in your data set, in our data set today, so you compute the average distance between for all data points in the same cluster. So for each data point, you take a data point in the same cluster, compute the average distance between that data point and all the other data points, and you do that for all data points in that cluster. Then you calculate the average. Then you take also the data point in the same cluster, then you do it to the data points that are closest to, do that to the closest cluster. So the cluster you are in, so compute the average distance for all data points in the closest cluster B for a certain data point. Then you calculate the average. Then from there, you can calculate the silhouette score. So basically, it's a very, very simple algorithm to implement, as you will see. So the silhouette score ranges from -1 to 1. And when it is 0, it means the data point is very close to the neighboring cluster, and that you may have some overlapping clusters. When it's 1, it means the data point is far away, and that is what we aim to achieve. The data point is far away from the neighboring clusters, in that you have very well-defined clusters, and the silhouette score is 1. Then when it is -1, then it means that the data point has been assigned to the wrong clusters, in that it is like having this 3.2 assigned to these clusters instead of this. So basically, that is what it means, that when the silhouette score is a -1 there. So by running this cell, you're able to get the silhouette score for each number of clusters. So if for 2 clusters, you get a silhouette score of around 0.95. That's a very good score. For 10, you get a silhouette score of about 0.6. It's not a bad score, but it's not the best among the lineup. So like before I go on, you can see that we converted the data frame with the actual data into an array, because like I say, we are dealing with 1 dimension. So you take the y-axis and leave around the x, because x is a deterministic stretch. So by running that, you can see that we have a silhouette score of two clusters. We are told that they have the highest silhouette score. So let's run that. Let's get to there. Let's have a plot. Oh, nice. So you can see that mine is the purple cluster. I don't know what color is yours, but mine is the purple cluster, is the main cluster. Then you have some random anomalies here. So we able to get rid of this, the red cluster here, because like I said, when I was starting, our main assumption is that the cluster with a few data points here is the anomalous cluster. So we aim to get rid of the red cluster and retain the purple cluster. So by running the next cell, our clusters are 2. By running the next cell, you can see that we have a histogram where we have the main cluster with around 1,634 data points with a mean of 0.35. Then we have our anomalous cluster with 50 data points with a mean of 0.92. So But by looking at this plot, you can actually note that there are some data points that are left out. So you might opt to increase the number of clusters from what that was stated by the silhouette score. So by just increasing the number of clusters, let's see what we get. I might go to 4. Oh, that's a bit nicer. You can see that we have a cyan cluster at the top, you have a red cluster, then you have a brown one, then you have the main one, which is purple, which is very well defined. So our aim is to get rid of the cyan one, the red, and the brown one, if I may say. So let's see the histogram for that. Oh, nice. So you have 28. You have another anomalous with 21. You have another anomalous with 25. So our main is reduced to 1,617. So that's a very good number of clusters, good number to work with. So 4 clusters. And let's get rid of those. So by running the next here, we're able to get rid of those anomalies and plot our stretch in that, like I said, each cluster is assigned a label. This is label 0, label 1, label 2, label 3. So on this code, you have the majority index. So you're able to retrieve the majority index from the labeled data set. In that, you have the majority index from the data set, from the k-means data set here. Then you can create a row using the pandas. Using pandas, you can create a column, sorry, not a row, column, and insert into your data frame. So, and you say that the data frame that is clean, you want to drop all rows where the k-means index is not the majority index. So with that, you are able to get rid of these classes, because when you drop all rows where the index is not equal to the majority index, it means that our majority index is 0. So drop everything that's not 0. And with that, you will retain all these data points. So, and with that, you can see that we have our stretch here running from, that is 11th June 2021 to 16th. That's around 5 days. So this is our clean data set, because you can see 1 or 2, actually 2 random data points. So if you want to get rid of these 2, you might opt to divide this data set, because 11th to 6th, those are 7, if I'm not 7 days. So you might opt to divide this into days and have smaller chunks. Instead of dealing with the whole set 7 days, divide it into days and have smaller chunks of the data set. And with that, you can actually get rid of each and every anomaly on the data set. So like this point and this point, which are left out. So with that, you can actually plot a mean. You can plot the mean here for each day. So you have on 11, we have a 0.36, on 12 at 0.35, and this is in meters, 0.36 meters. So you can have a bar plot of the same. So from 0.0 to 0.35, you can see here a bar plot from 11th to 16th, 6 days. So I said 6 days, sorry for that. So if you want, like I said, if you want to get rid of, to have a very, very clean one, we ought to divide the data set into pieces. So I have a question here. Okay, I'll deal with the first question. Do you just delete the anomalies or further analyze them separately? So for this demo, I just delete them from the data frame and just plot the clean one. But you might opt to analyze them further to know whether they are actually anomalies or they are not, because there are different kind of anomalies. You have like global anomalies, which just appear from the which are just appear from the rest. You have very contextual anomalies, where you have to decide, are they anomalies because they are anomalies because of a certain phenomena. So you have to decide what phenomena that is, so that you can actually classify them as an anomaly or not. So for this demo, we just delete them. We just consider them anomalies because I have prepared this data set. So like we measure the water level at very regular intervals physically. So we are able to decide that this is actually the main trend of the data. And these are actually anomalies brought about by effect on the actual, on the prototype, maybe a shake on the prototype, or maybe due to variations in environmental conditions. Maybe that. Tell me whether I've answered that question to your satisfaction. So the next one is, oh, thank you. So can we say that the best way to establish the number of clusters through visualization? Let me say visualization cannot be, let me say it cannot be the best way, because we have if you have a very small data set and you actually have an understanding of the data set yourself, you can actually use visualization if you understand the number of what clusters you may expect. If you know what clusters you may expect, you can actually use visualization. But if it is a large data set where you don't know what kind of clusters you may expect, you might opt using something like the silhouette score or the elbow method to decide the number of clusters that you want. But you can see that this is a data set that I collected. So maybe if I may say, I expect is a very well-defined trend of the data points here, like from on the 0.5 mark. So I expect what clusters to see, but in a completely new data set where you don't know what kind of data points are there, you might opt using the silhouette score or the elbow method that are provided on scikit-learn to decide on the number of clusters you may want to use for your data. Just let me know if you have answered your question. So let's go to the last part. Oh, thank you, Martin. So comparison with other relevant data sets. Like I said, water level data set maybe depend on other factors like rainfall. So we decided to compare our data set to rainfall data from TAMO. This is an organization that actually owns some weather stations in the watershed and also around the world, in Kenya also, and in Africa. So the Trans-African Hydrometeorological Observatory. So they are kind enough to provide us with the data, and we are able to compare it to our data set. And by plotting the data, you can actually see that there is a spike. There are random spikes after an increase in the amount of rainfall, but at this particular end here is a very interesting part of the data, in that there is a lot of rainfall. Yes, the spikes are there, but the water level is still low. So is there another factor that contributed to this? Now that is another area of research in this case. Basically, this is just a comparison at this stage. So for that, I'll stop sharing and maybe take you to where we are able to stream our data. Take you back to that. Maybe tell me whether you can actually see that. So basically, this is an app where you're able to visualize our data. This is raw data from the sensors in the field. We have 4 sensors currently deployed. We have been collecting data since February 2021. other data sets stretch about from 2019 or so. We have data from 2019, but we started out with the Moringato watershed in Nyeri 2021. So we have data from February 11th, 2021. This is one of our sensors, sensor 6. It's just a name. So you can actually see the water level trend when it was raining back in February in Nyeri, Kenya. We had some rise. You have very many anomalies here, so we employ the anomaly detection there. We have random anomalies all over, so but you can actually see the trend, the water level trend. As it rises, it falls all the way through the data. So this is live data, so you can actually see the last data point that came in. 12:22. Right now it's 12:30. So this is our last data point that came in. Then you can stretch back out to from February to October. So the data is still coming in from the sensor. You can actually see another sensor, sensor 2. Let's see whether it updates. Oh. Okay, this is sensor 2. You can see the data is still coming in. This is today, 5th of October. Our last data point at 12:30 just now. 12:30, 24 seconds, 0.77 meters. That is our sensor 2. You have a sensor 7, that's still down. Under maintenance, you have sensor 1. Data from 3rd October. Yeah. So basically, this is where we are able to visualize the data. On our clustering here, you can actually cluster the data for data and get rid of the anomalies. Like today, I cannot go with sensor 6. Let's see what it spits out. Oh, that was fast. So we have a mean of 0.21, and you can actually see the plot of the main cluster that contains the correct data points. So that is on the clustering. You can actually see the trend, the water level trend from February to now. And actually, you can also compare it with some rainfall data from Thermo. You have the weather stations, you can choose one and plot it out here. And also now you can actually download the data in terms of CSV. So, oh, I forgot to share the link. So the link to this web app on our GitHub repo. Let me just post it on the chart. That is the link to the web app, and you can actually see the data that is coming in from the sensor. So for now, I would like to end my presentation there. So thank you for your time, ladies and gentlemen, and keep the questions coming in. So I'd like to hand it off to my colleagues, Gabriel and Lorna. So thanks, Doc. Cheers.
Thank you very much. I see there are a number of questions there. I think you may want to handle them. Vinel asks, what tool have you used to set up your dashboard?
Oh, okay. So the tool that I've used, basically, that is Dash. Some like to call it Plotly Dash, but it is a Python package or module that can be used to set up applications, desktop applications to visualize the data. So that is what I use to set up this. Then I'm able to deploy that to a GCP cloud platform, and where it can be accessed by anyone, the app itself. So for your, maybe you can look into Plotly Dash just like
I think maybe you can put in the link.
Yeah. Maybe I'll post it later when I get the documentations to it. So yeah, just give me a minute. I'll do that.
And there is a question about, are all deployed sensors collecting the same information?
Yeah, so at this point, the sensors are different locations along the river collecting water level data. So in future, we aim to deploy some flow rate sensors and some turbidity sensors to collect those parameters also. But currently, we are just collecting the water level data at this point for all sensors.
Okay, so I see there's still other questions. What we may do is, let's just briefly go into the next part, and then if Jason, you can answer directly in the chat, or we'll come back to this during the breakout or later.
Okay. Okay. So see you.
Thanks.
Okay. No problem. So see you.
All right. So just before Gabriel takes over, I hope you can see what I'm sharing. Are you able to see the notebook? Okay, so
yes, sir.
What, right, great. So in the earlier session by Maria and Anani, they were talking about, you did a keyword spotting up. And perhaps maybe it was your first time to work with audio data, maybe not. But acoustic processing is quite an important area in IoT applications. That's why you saw even Edge Impulse have facilities for processing audio data. That's because the acoustic signal contains a lot of information. When you hear me speaking, you can, if you hear me maybe from yesterday and today, you can even identify my voice. You can tell what I'm saying. And so you can even tell to some extent, depending on how well you know a person, whether they're happy or not. So acoustic signals have a lot of information. The speech signal is the most dominantly used in acoustic processing, but there are other areas in IoT especially, where, for example, you're interested in developing an IoT gadget to even do cough detection, like we've seen in the COVID era during the pandemic. If you're trying to do fault diagnosis of machinery, if you're a very good driver, you probably know, you'll hear your engine and you may say, well, I think there's something wrong with it today or something like that. That is using the acoustic signal to do fault diagnosis. You may also want to do noise pollution monitoring or something like that. So in the notebook, what we want in the acoustic audio processing notebook, what we want to do is just a little bit of introduction on how to process audio signals. So I hope you're able to get it, to get the notebook. And we'll be using a library known as DSA, which is very useful in processing audio signals. So I won't go too much into the physics, but really what ends up happening is that when you're producing sounds are vibrations. Those vibrations end up being made into variations of air pressure, and that's picked up by your microphone. So in the first cell of this notebook, where we are going to interact with an acoustic signal before Gabriel shows you the acoustic processing application in ecosystem monitoring, the first cell allows us to import the libraries we need. DSA is, as I mentioned again, I think this is a go-to tool for acoustic processing now. So then in the next cell, what I want to do initially is, audio signals are no good if you're not hearing them. So what I want us to do as our audio examples will be some musical instruments. So I'll need to change the way I'm interacting. I've removed the earphones. Can you still hear me?
Yes, sir, we can.
Yeah.
Okay, so in the next cell, there are a few audio examples. So for example, and they're all playing one note, one musical note. and that note vibrates at 1046 hertz. So we have a piano, violin, trumpet. So if we choose the piano, this third cell here loads the audio signal. So what it does is that it picks up the signal, which is a sequence of samples, and also picks up what is known as the sampling rate. This quantity sampling rate is how fast the samples of the sound are being collected. We saw a bit of that in the earlier lecture, where we saw some signals are being collected at 5 hertz or 16 kilohertz. And so the audio signal needs to be collected at a fairly rapid rate. So we end up, we'll be able to determine how fast they're being collected for this particular audio application. So in the next cell, you can actually hear. So I'll play this, and remember, so that's, I hope it wasn't too loud for you. That was a piano. If we then load something else, a flute, okay, so you can play around with that, but let me pick the piano because it makes the rest of the notebook quite easy to do. So after you hear that, you can also visualize the audio samples. So these are the audio samples, and as you heard, the piano starts off as a high sound, and then it decays. So that's what you're seeing visually. And the sampling rate, so these are the actual samples we are visualizing. The sampling rate is 11,025 hertz, or 11.025 kilohertz. And if we view the first few samples, you see they are stored as floating points. So these are the sample values. So there we are. Now, audio signals like this need to be, when they are processed, you need to zoom in and process smaller chunks of audio. So for example, the entire audio signal here, is 1 second. So on the x-axis, you have the time, it's 1 second. 1 second is too large for us to process. The reason being that the characteristics of the signal are changing over time. So we need to zoom in. So when we zoom in, let's say we want to work with a segment that's 10 milliseconds or 10 to the minus 3 seconds, that's 10 milliseconds. And we select a random chunk. So this piece of code gets a random segment of 10 seconds. If I process it, maybe you'll notice that every time I run that cell, the signal looks a bit different. I mean, it looks different from segment to segment, but within the segment, there's a lot of similarity. Do you see that? Now, that is the reason why we zoom in, because if we assume that the properties of the signal are the same over the whole signal, it's not true. It's not true. So we need to zoom into smaller chunks, and here we are zooming into 10 milliseconds. So we are saying all this to say that in audio processing applications, there are some parameters we need to select, like how big our window sizes will be. And the reason we need to zoom in is because of time, is because of the variations from segment to segment. Another thing is the fact that we don't often process audio signals in this domain where we are looking at the samples directly. We move into the frequency domain. And that is, if you look at this number here, we are saying that this signal varies, the variation is at 1046 hertz. That's a notion of frequency. So what we do is we transform the audio signals by a process known as taking a fast Fourier transform. I won't bore you with the signal processing details, but we can talk about that later. But in essence, allows you to transform the time domain or the sequence of samples into something in the frequency domain, something like you can characterize in terms of hertz. So to do that in Librosa, what you need to do are set parameters like the window length and the overlap. Overlap is how much overlap there'll be between neighboring segments. This is a common practice in audio processing applications. So if we run that cell, what we see is the audio signal turned into a picture. And I can help you interpret what's happening here. The x-axis is time and the y-axis is frequency. And this picture is telling us the energy. So the energy ranging from -80 to 0. So 0 is the high energy and light color. And it's saying that that energy is concentrated around 1,000. 1,000. So we actually know that it's 1046. So there's a spectral peak there. We call it a spectral peak. But in essence, the audio signal that you had of the piano has been turned into a picture. Okay, and that is very useful for machine learning because then we can put this into neural networks. So we can look at the shape of our spectrogram. This is what you'll hear called a spectrogram. So this picture. The thing is that the picture is not is quite large. So really S is a matrix of values. And we sometimes need to reduce the dimensionality. So what we do is we use a MEL frequency bank. And you may have heard of the MFCCs in the previous lecture, MEL frequency capital coefficients. These are parameters, these are reduced. So we pass this picture through what is known as a filter bank, and we lose some resolution. So if we say that we want 32 filter banks, we'll end up with this sort of picture. This is now called a MEL spectrogram as opposed to a spectrogram. You'll see that on the x-axis, you have less resolution. So the pixels on the on the y-axis are wider. But for a lot of applications, this will suffice. And what will end up happening is that you have a smaller feature, and that is always useful in machine learning because that will mean your models are smaller. I know we've gone a bit fast through that, but it's because I want Gabriel to take over and go into an application of acoustic processing that we've developed for ecosystem processing. And maybe what I'll do is I'll stop sharing and maybe take one question if there is any. If not, I don't see any question on the chat. Gabriel, maybe you can proceed, but I'm happy to take any question as Gabriel is setting up. Any?
Hello, everyone. So if we have no questions, let's proceed to the acoustic monitoring notebook, the acoustic ecosystem monitoring notebook. So I hope everyone has filed the notebook. Let's proceed from there. So we have said that sound is one form of communication that is used by human beings. That is during the last presentation. So, and the sound contains a lot of information that we can use to describe different scenarios. So same case, our ecosystems contain a lot of acoustic data that tell a lot about what is happening in them. So if you take a walk in a park, you will hear a lot of sound. If there's human activity, you can be able to tell. You can hear birds, you can hear elephants, and all that. So if you can be able to use that sound to analyze the activities that are taking place in the ecosystem, so that would be a good application of acoustic processing. So traditionally, when we are monitoring ecosystem, we carry out physical surveys. These physical surveys are expensive and are limited by other factors, such as inaccessibility of some parts of ecosystems. And with the current trends in ecosystem degradation, we need to increase the rate at which we are monitoring our ecosystems in order to preserve biodiversity. So one method of monitoring our ecosystem that can help us is acoustic monitoring, whereby you deploy acoustic sensors in the ecosystem, they collect acoustic data, you analyze that data, and then you are able to tell, to monitor the trends in them. So in this case, we'll be dealing with birds. The reason we are dealing with birds is, one, birds respond quickly to changes taking place in their habitats. Therefore, if you monitor birds, you can be able to tell a lot about the other species. And this is what ecologists refer to as an indicator species. Also, birds vocalize a lot. So therefore, acoustic monitoring of ecosystem will suitably work well with them. So in this notebook, we'll be dealing with 3 species of birds that are found in Kenya. That is the hat-lapped sturacol, the tropical bubu, and the grey-backed Camaroptera. So our intention is to show how we can be able to classify these birds just from their sound. So we'll be using data from our local deployment and from Xenocanto, which is a public website where people upload sounds of birds. So let's proceed to the first cell and import the necessary libraries. So I hope everyone is at the notebook. Okay. So now let's load the parameters that we are going to be processing our sound with. That is the kind of mail spectrograms we'll be generating, the duration of the sound that we'll be processing. That is the blocks, as has been talked about in the previous presentation. So in the next 3 cells, we are going to load sample files and play back. So I'm going to play one of these files so that you can listen. You can also try it on your site. So that's one bird. Let's proceed to the next cell and load the other. And finally, so you've had the 3 audio samples, and you can tell by just listening that they sound differently. So if you had prior knowledge of how the 3 species that I've talked about sound, you can be able to identify them by just listening to them. So now our intention is to enable digital computers to do the same, that is, listen to and then be able to tell different species. And that's when the concept of acoustic classification of birds comes in. So this field of acoustic classification of birds is very interesting. It's for ecosystem conservation, ornithology, and also for bird watchers. So when we talk about acoustic classification of the collected acoustic data, we collect a lot of data when we deploy acoustic sensors. So if we follow the route of manual classification, this may tend to be cumbersome. And so we may opt to introduce sampling, which will introduce incompleteness and bias. So to solve this, we perform automatic acoustic classification of birds, whereby you develop acoustic sensors that are able to capture acoustic sound, process the sound, and be able to do the classification for you. So what you get is the classification of the captured sounds. So however, this automatic acoustic classification is faced by several hurdles. That is limited annotated data per species, background noise in the captured sound recordings. So also, for example, from Xenocanto, you have different people uploading different sounds from different places. So the sound that they upload will have variable length. So if you intend to process that sound, you'll have to deal with variable length. And also, you get that in some instances, you'll have multiple birds singing in the same recording. So let me talk about how we collect our own data. So for machine learning, you need data to train models. So we developed a Raspberry Pi based acoustic sensor, as you can see here. So we have the battery to power the system. The system is housed in an adapter box. We have a microphone to capture the sound, and we have a power supply that was designed here to power the system intelligently. So remember, when you're deploying sensors in the field, power is one of the most important factors to consider. So, and the Raspberry Pi, as we talked about earlier, is a single board computer. So you don't want to shut it down using unconventional methods out of the batteries running down. So we have developed a power supply board to intelligently power the Raspberry Pi. So it's able to monitor the battery powering the system and make informed decisions on when to shut down the system, waiting for the system to be recharged. So this is the system deployed at the Conservancy. It's solar powered. You can see the system is out. The system is inside this adapter box. We have the microphone protruding and a mounting mast. So now let's go back to the problems that we're talking about. So to achieve reasonable results from the data that we are going to collect from this system that will have those problems that we have talked about, we need to manipulate the data that we get. So, and to achieve this, we perform data pre-processing and data augmentation on the data collected. So let me begin with data pre-processing. So for this task, we first dealt with the problem of having background noise in the sound. And to do this, we performed audio noise separation based on the concept presented in the paper in bold here. So, and to achieve signal audio noise separation, what we did is we computed the spectrograms. And then the idea is that those parts of the sound that correspond to the signal is now the part where we have bird singing, and the noise is the part where we have either background noise or silence. So those parts that will have will have bird singing will exhibit high energy compared to those that do not have bird singing. So to separate these parts, we use the energy. That is, we compute the spectrograms, pass it through the signal noise separation algorithms to obtain this. And you can see that in this spectrogram, the spectrogram to the right is more dirtier, and the spectrogram to the left, you can see the features, which are the lines that are moving up and down the spectrogram, and those are the features of interest. Now, so we've said that when we are using sound to perform machine learning application, mostly we don't deal with sound in raw form. So we extract features from it, that is this frequency component of the sound, and plot either spectrograms or mass spectrograms that are fed to machine learning models. So in this case, we'll be working with the spectrograms using 40 channels. So let's compute mail spectrograms of the audio samples that we were playing up there and visualize them. So let's run this cell. So now, if you can observe the spectrograms that you obtain, this is for the greybacked Camaroptera, this is for the heart-lab Strako, and this is for the tropical bubu. So visually, you can tell the difference. This is because of the difference in the frequency component of the different sounds of the given birds. So now if we can treat this as our inputs to machine learning models, we can be able to classify the birds from their vocalization. Now, let's proceed to another solution that we used in solving the problems that we encountered during acoustic classification of birds. And this is audio padding. So you get that due to variable length of recordings, you need fixed length of recordings to fit your machine learning models. So some audio files will have lengths that are below the one that you have set as the threshold. So to solve this problem, you pad the audio with noise, and this actually improves the performance of your system. Since you expose it to the noise it will be expecting in the field. So the noise that we use is the noise that was obtained during the audio noise separation. So you pick a random noise, pad it to the sound, and then feed that padded spectrogram to the machine learning model. So here is an audio file that is less than 3 seconds long. We intend it to be 3 seconds long. We pad it with noise, and you can observe at the end, there is this new feature that has been added, that is noise. So for this task, we were working with simple models. We did not fit the mel spectrograms directly, so we proceeded to generate more features from them. So, and the features that we were working with are the mean and the standard deviation of the frequency channel. So now let's proceed. Let us visualize the features that I'm talking about. So, and by running the cell, this cell. So you get that depending on the energy concentration, where the energy is exhibited on the spectrogram, you'll have a different mean and standard deviation extracted from that spectrogram. And this can be, we can leverage this as a feature to fit our machine learning model. So you can see for the greybacked Camaroptera, the mean is and since the energy of was concentrated at higher frequency, it's at around the 30th channel. For the heart-lab Strako, it was a bit lower, and it's at around the 10th channel. For the tropical bubu, you also noted that there were two kind of streaks, and you can see two spikes here. So these are unique features that a machine learning model can learn and be able to classify birds from their vocalization. So and these are what we used for the models we'll be talking about in this notebook. So the models I'm talking about, we developed simple models before proceeding to using the deep neural network machine learning models. So and these are the baseline models, and a baseline model can be defined as a model that achieves reasonable result, and it's simple to model and train. Also, they give you they help you to rate the performance of the other complex models. And the models that I used for these tasks are linear support vector classifier, the support vector classifier, the multi-layer perceptron classifier, and the random forest classifier. So we'll be seeing the performance of these models on our data. So let's import the libraries that we'll be needing by running that cell. And now the cells that below contain functions that were developed to achieve this task. So this function is used to extract the MEL spectrograms of the files. We have the MEL spectrograms that we downloaded from downloading as per the instructions that were in the repo. So in this cell, we are going to split the MEL spectrograms into chunks. And this will help us in solving the problems of limited data per species. So from one audio file, we can be able to extract more features that we feed to a machine learning model. So the next function, we are going to split the chunks that we have generated into training and validation data. So in the cell that the function below that, the train models, is for training the machine learning models. And then the function below that, we are going to test the models that we have trained using sample test data. So let's run the cell. So to train the machine learning models, let's run this cell. And wait for the models to be trained. On my machine, it was pretty fast, so depending on. Now let's proceed to test the trained models using random test data. By running this cell and then using this drop down, you can choose a model and test its performance. So we have the predicted species is the HeartLab Struraco, and the expected species was HeartLab Struraco. That is using the linear support vector classifier. Using the random forest classifier, we picked a random file that is the gray-backed file that contained a gray-backed Camaroptera. So we predicted the species to be gray-backed Camaroptera, and that's what we expected. Let's proceed to the SVM RBF. Still the file that was randomly picked was gray-backed Camaroptera. Let's use the multi-layer perceptron. So we picked a file that contained a tropical boo-boo, and we predicted a tropical boo-boo. So you can hover over the models and see how they are performing. So we have some errors at some point. Hello, Chisenga. The issue with missing file is there was a change in the repository that you were to pull to update. That's why you're getting that error. So kindly pull to make that change and then try again.
Okay, Gabriel.
Yeah.
Thank you very much. I think we can take some questions, and then we had another session planned with camera trap data, which we can't unfortunately get to right now. Maybe we can just take questions and we can push everything between now and 11 and 12:15, and then move on to the next presentation. That would be my suggestion, because I know we've covered quite a bit, and maybe let's just maybe take those 4 minutes for discussion, and then push everything to the afternoon session. How does that sound?
That's okay.
So questions on the chat, and yeah, we can talk more in the afternoon.
I can see that the repo has been shared. Yeah.
Okay, we had 2 minutes left, but there's a question. Maybe Gabriel, you can answer this? Does audio level some way impact the input signal?
Yes, it does. That's for that case. You get that. Okay. Depending on the acoustic environment being, for example, if you have the audio was collected far away from the microphone, another one was collected closer to the microphone, so the plots of the spectrograms will be a bit different. So therefore, I would say that the level of sound may somehow affect the performance of the machine learning models. You may get that sound that was captured very far, the machine learning model is not able to identify it correctly if it was trained with data that was picked at cross-range. I hope that answers the question.
Okay, I think we can end there, and thank you very much for your time. We'll hand over back to you, Hannah, to introduce the next speaker.
Okay, thank you so much. Thank you. And can you please give a round of applause one more time for the IoT workshop team? Okay, thank you so much. So for the next session, we'll be moving on to a live workshop by Ms. Manuel.
Hello, Hina. How are you? Yes, this is Manal Jalloul.
Good day, ma'am.
Yes, how are you, Hina?
I'm finding yourself, ma'am.
Okay, so I'm gonna start sharing my slides.
Okay, that's not a problem. Thank you.
Thank you. So I hope everybody can see my screen. So welcome. This is a workshop provided by NVIDIA Deep Learning Institute, and this is the fundamentals of accelerated data science with Rapids. Before I start, I'm gonna humbly present myself. I'm Dr. Manal Jalloul, and I am a lecturer and researcher at the American University of Beirut at the Department of Electrical and Computer Engineering. I'm also a certified trainer and university ambassador with the NVIDIA Deep Learning Institute. Also the founder and CEO of AI Labs, Digital Hub and Solutions. So first, I'm going to tell you a little bit about NVIDIA Deep Learning Institute. So we are NVIDIA Deep Learning Institute provides hands-on trainings and workshops for scientists and researchers on how to use deep learning and accelerated computing to solve real-world problems across a wide range of domains. And to do that, we provide access to GPU-accelerated workstations in the cloud, where you will be able to learn how to train, optimize, and deploy neural networks using the latest tools and frameworks. This workshop today that we will going through is provided by NVIDIA Deep Learning Institute. Now, in NVIDIA DLI, we also provide a plethora of trainings and workshops spanning different domains, from autonomous vehicles to finance to healthcare genomics, image analysis, video creation. We have trained more than 120,000 developers worldwide, and our trainings can be offered either online or in an actual classroom environment, in either a self-paced version or instructor-led by our instructors. AI Lab, on the other hand, the company I'm leading is an artificial intelligence company based in Beirut, and we are the official delivery partners of NVIDIA Deep Learning Institute Educational Services in the MEA. So with that, we go back to our workshop, which is Rapids and the fundamental of Rapids. So Rapids is a suite of open source software tools and libraries and APIs that give you the ability to accelerate end-to-end data science pipelines completely on the GPU. So it is licensed under Apache 2.0. Rapids is incubated by NVIDIA based on extensive hardware and data science experience. And in this workshop, we hope that you will learn the core tools to use Rapids for everyday data science, and to understand rapid scalability from workstation and cluster to cloud and HPC. So hopefully you will be able to build the foundations for you to learn Rapids capabilities now and in the future. So today's data science problems actually demand a dramatic increase in the size of data, as well as in the computational power required to process all of this data. And since the ends of Moore's law, that's meant that handling large data sizes in today's data science ecosystem requires scaling up to multiple CPUs or even going to GPU acceleration. Now, here in this slide, we see the classic GPU acceleration problem, where I have two applications, application A and application B. Each of them use GPUs for its own acceleration, for its own purpose. Now, the problem is that if I need to move the data from app A to app B, I have this gross data pipeline where first I have to move the data to the GPU to provide acceleration for app A, for example. But then if I want to move the data back to app B, I need to move the data from the GPU back to the CPU to do copy and convert in order to put the data in the proper format to be consumed by app B. And then if app B requires acceleration, I have to copy the data back to the GPU with the needed copy and convert operations. So as you see here, the set of copy and convert pipelines actually consumes more than 99% of whatever you are trying to do in app A or app B. So you end up losing any kind of acceleration that you may try to achieve. So one of the questions and the reasons why we have Rapids today is to answer this question. So what if we could actually keep the data on the GPU and eliminate all kinds of copies back and forth to the CPU? So what if we could go from app A to app B without the need for any copy convert operations? So how could we move between applications or different stages of the data science pipeline and keep the data completely on the GPU? Well, to address these challenges of the modern day data science pipeline, NVIDIA announced Rapids. So Rapids is the suite of open source software libraries that will allow you to perform the entire pipeline of data science and analytics completely in the GPU. And therefore, it aims to accelerate the entire data science pipeline, including data loading, ETL, model training, and inference. Now, this will enable more productive, interactive, and exploratory workflows. So this is Rapids. The Rapids addresses this by design. It provides a columnar data structure based on the Apache Arrow columnar format on the GPU, and this format is called the GPU data frame. And to work with GPU's data frame, Rapids provide a suite of GPU accelerated libraries, and one of them is this QDF, or which is a pandas-like API that allows to do data handling and preparation. And what's really attractive about it is that each one of these GPU accelerated libraries is actually equivalent to the CPU version, so that Python programmers will have, will face zero difficulty learning Rapids and providing acceleration to their applications. And more than that, Rapids actually provides integration with deep learning libraries by providing a native support for array interface. Now, this means that data that are stored in the Apache Arrow format will be able to be ingested and consumed by deep learning frameworks that support the array interface as well. So these are the set of tools and APIs that are provided by Rapids. So we start by looking at the Pandas, for example. So Pandas is this fast and powerful and flexible, easy to use open source library for data analysis and manipulation on the CPU. Now Rapids provides an API that is very, very similar to Pandas. However, it's completely GPU accelerated, and it's called a QDF. This QDF is a Pandas-like API. It allows to manipulate, filter, aggregate, load, join data sets, similar to what Pandas does, but all of these operations are natively accelerated on the GPU. Now, on top of QDF, we have QML, which is a scikit-learn similar API. So scikit-learn, as you know, is a library of machine learning algorithms executed on the CPU. Now, QML is this API provided by Rapids that provides a GPU-accelerated version of scikit-learn. It contains machine learning algorithms that will be executed on the GPU. Similarly, we have QGraph, which is a NetworkX API for graph analytics. On top of these libraries, we also have QXFilter that provides a GPU-accelerated visualization. It is a GPU equivalent API to Bokeh or Data Shader that's usually executed on the CPU. For geospatial analysis, we have QSpatial that is equivalent to GeoPandas or Scikit-Spatial. But again, QSpatial provides GPU acceleration. We have QSignal that provides GPU-accelerated API to Scikit-Pi signal. We have CLX equivalent to CyberPandas, but with GPU acceleration. So what are the requirements to install Rapids? Well, first of all, in terms of operating systems, you will need one of these 3 operating systems. And what you also need is a GPU, NVIDIA's GPU, Pascal architecture, or newer. You need an updated version of CUDA. Now, Rapids does adopt an open source flexible mindset. We have new versions that are released regularly. For the sake of this workshop, that you will have access to today, we are using version 0.15, but we have a newer version coming up in the near future. So you may ask yourselves how we can download Rapids. Well, there are 3 different ways to downloading Rapids. First of all, Rapids is open source. So you may find the source code for Rapids on GitHub. You go to github.com/rapidsai. However, this is not really my advisable way of downloading Rapids unless you have, a certain functionality that you'd like to improve on. Otherwise, the preferred method to download Rapids is to download a container from NVIDIA's NGC. So NVIDIA's NGC is NVIDIA's GPU cloud. This is a containers registry provided by NVIDIA. This is you can have free access to NGC, and within NGC, you can have access to more than 50 different containers that span deep learning frameworks, pre-trained models, as well as data science workflows. So you may go to NGC and download an efficient, optimized container for Rapids that is easy and ready to run. Now, a third option, you could also download the Rapids by using Conda and pip. Now, after downloading Rapids, you may also ask yourselves where you can actually run it, where Rapids supports all NVIDIA GPU cards, Pascal architecture or newer. That means that you may have maybe a Titan X Pascal graphics card, or the new Volta V100, or even a DGX1, DGX Station, or a DGX2 server, all with the Pascal or newer architectures. These support having Rapids installed on them. Rapids can also be deployed on any of the most famous cloud providers like Google Cloud, Microsoft Azure, and Amazon Web Servers. So in the workshop, the problem that you will be working on is actually simulating an epidemic that hits the population in the UK. We have a set of different fused and simulated data sets that are fused from different sources. We have a population data set, which is simulated from the UK consensus data on England and Wales. And it is a detailed data set of the population, including the age, sex, given name, and country, as well as the aggregate statistics like spanning geographic coordinates, employment, and so on. We also have the road network data, the detailed road network data of the UK, England, and Wales. We have the nodes, endpoints, and junctions data, as well as the edges of the entire road network of Great Britain. We have epidemic data that span detailed hospital and clinic data from the UK National Health Service, and And this data set is actually simulated based on academic research on the Ebola risk factors. So this is the data set that will be provided for you in the workshop to carry out the different hands-on exercises using the RAPIDS libraries to appreciate the acceleration provided by RAPIDS as compared to CPU-like APIs. So first of all, I'm going to show you how you can actually access this hands-on course. So here you see in this slide the different steps that you have to go through in order to access the hands-on course. So in this hands-on course, you will be given access to GPU accelerated server in the cloud, as well as to the notebook, a Jupyter Notebook environment to carry out the hands-on exercises. So what you have to do is to go to courses.nvidia.com/DLI events. You'll have to log in with your developer account. So this is a requirement here to create a developer account and then log in with the developer account that you have created. And then you have this event code that you have entered. Okay, so I do advise you here at this step to record the event code and maybe I can share it in the chats. So I'm going to actually stop sharing here my slides and guide you through the hands-on environment and just show you how you can access the course and how it looks like. And then we go back to resume the rest of my slides. So I'm going to, do a new share here, and I'm going to hop into. So let me. So stop share here. I'm gonna Google Chrome and I'm gonna show you how the course looks like. So I hope you can see my Google Chrome screen. So the way to access the course is as follows. First, you have to go to courses.nvidia.com/DLI events. And notice here that you will need to sign on with your developer account. So if you don't have a developer account, you will see a sign in or log in sign over here. Here you have to click on it. You have to create a developer account. And then you log in with your developer account. So when you go to courses.nvidia.com/DLI event, you should see your name over here at the top right of the screen. Okay, so once you do that, and if you have your name there, you can enter the code, the event code for this training, and it is actually DSA. So let me go here. So the event code is actually, okay. This is it. So you make it recorded. So it is DSA. I'm going to share it on the chats. Okay, so that everybody can have it. So this is the event code. So let's see. Okay, so you have to go to courses.nvidia.com/DLI-events. And after you go there, you have to enter this event code. And you enter the event code. I think it's typed twice, so. Okay, so I hope this is clear. I'm going to delete this account. Okay, so you go to courses.nvidia.com and /DLI event, and you should be able to see the event code just over there. You log in with your developer account and you enter the event code. And once that happens, then you will be able to access the online course or the online workshop. Now make sure that you use Google Chrome and not Safari. You will face problems if you're using Safari. So make sure that you are using preferably Google Chrome for running the workshop. So once you log in, or you enroll in the course, then this will take you to this launch page of the course. So you'll be guided towards this page of the course, and then you'll have to go to this course tab to get started. Now, this workshop is made up of 3 sections. So this is designed to be a self-paced workshop. We will not be able to go through the workshop during our 1-hour session today, but by having access to this workshop, you'll be able to work on it on your own at home, at your own convenient time. It is a self-paced course designed for that purpose. So with the way to access the Jupyter notebooks, so again, this workshop is made up of 3 sections. We have the GPU accelerated data manipulation section, the GPU accelerated machine learning section, and a final project with biodefense. So you're going to start with the first section. So once you are in the first section, there's a start tab over here. Now, if you press the start tab, you're going to wait a few minutes, and these minutes are needed in order to launch a GPU in the cloud in the background for you. So please be patient for the environment to load, because this means, and during this time, all the libraries needed, the data sets that are needed will be loaded into a GPU instant in the cloud for you to use during the training. So once that starts done, you can launch the task by pressing this button, Launch tab, and this will allow you to access the Jupyter Notebook or Jupyter Lab environment. And I've started it before the session here. So you will reach the Jupyter Notebook environment where you have a series of exercises and Jupyter Notebooks to go through. Okay, so if you are going with me through this process and your instance is still loading, I'm going to stop sharing here and go back to the rest of my slides, and then we can revisit the notebooks again and maybe work on the first notebook together. Okay, so I'm going to stop sharing here and go back to my slides. Okay, again, if you have any question, kindly type it in the chat. Okay, so I'm going to go back to my slides and to resume where we've left. So again, this is how you can access the training, and once you have access to the training, this training will be there on your dashboard. So next time, if you log in with your developer account into NVIDIA, then you will find this course in your dashboard. You can always take the course again another time, resume the course at your own convenient time. So you don't have to finish the entire workshop in one setting. You can always come back to it, redo some of the exercises, or to re-emphasize a certain point that you still don't understand. Okay, so going back, so in this workshop you will get hands-on experience with the different components of Rapids. As a start, in the first with Jupyter Notebook, you will have hands-on experience with the QDF, and as we said, QDF is this a GPU accelerated library for that has an API similar to Pandas, and it is based actually on the Apache Arrow columnar format, and it uses the Rapids format, data frame format, in order to do loading, aggregating, filtering, and manipulating of the data completely on the GPU. Now, in the Jupyter Notebook of the workshop, you will be able to compare the performance of Pandas with the QDF, and you will see that QDF actually provides 100 times acceleration for the different data operations as compared to Panda using Pandas. So you will be able to measure the times of running Pandas versus running a QDF on the data set that is provided, which will allow you to appreciate the advantage of using QDF as compared to Pandas in order to provide GPU acceleration to your application. So, and again, all of this, as we said, Rapids, the entire libraries of Rapids are built on top of the Apache Arrow columnar format. So the Apache Arrow is actually a cross-language development platform. And for in-memory analytics, this is an open source standard that allows interoperability with a wide array of systems, including non-GPUs and non-Rapids. So as you see here for this particular data frame, data is stored in the memory according to the columnar format. So this is what the Apache Arrow uses, columnar format for in-memory analytics. So the Apache Arrow is this open source standard that defines a language independent columnar format for flat and hierarchical data. So this is the format that is adopted by Rapids, and as I said, the main advantage of that is that it will allow for interoperability with different array of systems, including non-GPUs and even non-Rapids. So the Apache Arrow allows for this efficiency and interoperability between the libraries accelerated by Rapids, as well as other libraries in the data science ecosystem. Even if they are non-GPU or even non-Rapids, we still have interoperability between them. So I guess maybe if you're just following up with me and you've been able to launch your Jupyter Notebook environment and maybe access the course, I'm going to just guide you through a little bit the first couple of notebooks. So I'm going to stop sharing here and share again my Jupyter Notebook environment for this training, and just guide you through the environment and what you will see here. So as you see here, what we are using is the Jupyter Lab environment in order to carry out our hands-on workshop. So in this workshop, you have actually access to 4 NVIDIA V100 GPU accelerated in the cloud. So by giving you access to this workshop, you are also given access to a virtual machine backed up by 4 NVIDIA V100 GPUs and with all the libraries that are needed for you. So we have these set of notebooks that you are required to go through to allow you to get experience with Rapids. Now, some points to consider while running these notebooks is that at any point of time, you can actually check check, the available GPUs in your system, their current memory usage, and any processes that are utilizing them by running the magic command NVIDIA-SMI. So at any point in time, you can run this cell in order to monitor the status of your GPUs and to see the consumption, the memory usage of the available CPUs to you. Okay, so I'm going to just continue while this cell is being run. So also, I'm sure you're familiar with the magic commands time and load that allows you to time the code, the different steps in your environment. We're going to be needing to do that in order to compare the performance of Rapids with other libraries that execute normally on the CPU. Now it seems that this is taking a long time, so I'm going to just try to run it again or restart the kernel. So at any point in time in your environment, if you're facing any issue, if you're facing any error, you can always restart the kernel. So I'm gonna just restart the kernel here. Okay, now the kernel that we are using for every notebook uses its own kernel, and it will have its own memory allocated to it. At any point in time, if you're facing a difficulty in a kernel, you can always go to this kernel menu and restart the kernel. So I'm going to run this cell again. Okay, so I'm going to go forward while this step is being executed. So, and as I said, each one of these notebooks will have its own kernel, and it will actually consume, and the kernel will use a part of the GPU memory. It's very important that whenever you want to move from one kernel to another, that you restart the kernel in order to avoid the risk of, exceeding the allocated GPU memory. I have a question from Dina. Are certificates going to be issued. Yes, there are certificates for you for this course. So once you complete this course, there's an assessment at the end of the course. And once you complete the assessment, you will be able to receive a certificate for this course straight from NVIDIA's Deep Learning Institute. So going back here, as I said, it's very important at the end of every kernel to shut down the kernel or restart the kernel because you want to avoid consuming too much of the GPU memory. Because as you know, here we are dealing with very, very big data set, and it's very easy that we, you know, in a particular kernel overload the GPU's memory. So if you want, whenever you want to use from one kernel, move from one kernel to another, it's advisable that you restart the kernel. Now, there are different ways to do that. You can either run the code cell that is available at the end of every kernel, which allows you to shut down that kernel of that particular notebook. Or another method is to go here and check the running kernels and just, you know, you may shut them down all, okay, if you want. This ensures that you've shutted that particular kernel. Now, here in this notebook, you're gonna start working with the basics. You know, you're gonna be introduced to QDF, and as I said, this is the GPU accelerated library from Rapids that is similar to Pandas for data manipulation. So you'll be able in this notebook to explore the functionalities of QDF, to load data from disk, and throughout the process, you'll be able to compare it to Pandas. So you'll be able to compare the performance of QDF to Pandas and to measure the times of these operations for reading from file, also from writing to file. And you'll also be able to see how actually QDF has an API that is very, very similar to Pandas. So whatever you can do with Pandas, you can do with QDF with the same commands. So you will be able with this exercise here to do kind of a exploration of the functionalities of QDF and its basic operations that you could do. And again, all the time you'll be able to compare the performance of QDF with the Pandas equivalent functions. Okay, so I'll leave it to you to go through this notebook as well as the rest of the notebooks to familiarize with yourself with the data manipulation libraries provided by Rapid. So with here, I'm going to stop sharing. So I hope that you are familiar now of how to access the online workshop, how to access the Jupyter Lab environment, and to go through the exercises. So as I told you, this course is made up of 3 sections. So once you're done with the data manipulation, so the data manipulation is one Jupyter Lab. Once you're done with it, you're going to go to the next task with the GPU accelerated machine learning. There are a set of notebooks there that you'll have to complete, and then the project defense. And notice here, there's an assessment in this particular task of the workshop. If you're able to finish this assessment successfully, a certificate from NVIDIA will be automatically generated and provided for you. So I'm going to go back to my slides to share the rest of my slides there. Okay, so as I said, Rapids also one of the in this workshop you're going to actually have experience with all the libraries that are provided by Rapids. So as I said, Rapids also has this library called the QGraph, and QGraph follows the Network X convention for manipulating graphs. And in this workshop, you'll be able to build up a graph using the from QDF edge list function. And you're going to compare this to the CPU version, and you're going to appreciate the massive acceleration that you're going to get from using QGraph as compared to the CPU Network X library. So you're going to explore the functionalities of QGraph for graph algorithms and graph manipulations. And you will see that this library will be able to consume Rapid's GPU data frames, consume the data there in order to manipulate graph objects. Rapids also supports a library called Dask. And for those of you not familiar with Dask, well, Dask is is a parallel computing library. And the advantage of Dask is that in addition to using multiple CPUs or to execute computational graphs in parallel, Dask schedulers allow us to parallelize our operations across multiple CPU cores, multiple CPUs, and even multiple GPUs. So the Rapids platform will be using Dask under the hood in order to distribute data frame operation to multiple GPUs. The way Dask works is by dividing a data frame into multiple partitions, where every partition will be scheduled on a different GPU, and Dask schedulers under the hood will also partition the operations that will be executed on these partitions across the different available execution or computing resources. This allows Dask to seamlessly be able to scale across the available GPUs as well as CPUs, and this allows you to manipulate data sets that are very large and they may not fit into the memory of a single GPU. You will also have, in the second part of the workshop, have hands-on experience with QML, and QML is the library for GPU-accelerated machine learning algorithms. It follows the scikit-learn convention. It uses an API exactly the same as scikit-learn. You will see that with minimal code change, you'll be able to convert your code from using scikit-learn to QML, and you're going to notice by measuring the times massive acceleration that this will result in. In this workshop, you'll be able to have hands-on experience with k-means, dbscan, logistic regression, k-nearest neighbors algorithms, as well as XGBoost. So k-means is this unsupervised clustering algorithm. You'll be able to experiment with it, as well as the dbscan clustering algorithm. You'll have hands-on experience with the k-nearest neighbors algorithm, as well as the logistic regression and XGBoost. So in conclusion, I'll have to say that Rapids is this open source software tools and libraries that will allow you to accelerate the entire data science pipeline completely on the GPU. It allows you the freedom to do everything, starting from data loading all the way to maybe even deep learning frameworks completely on the GPU. And as a result of that, massive acceleration can be gained. Rapids could be implemented at every scale, from workstations and clusters to cloud and HPC. It supports, remember, it can support any NVIDIA GPU card as long as it is a Pascal architecture or more. So whether you have a Xavier NX, a Jetson Xavier, or even one of the latest E100 tensor boards, you'll be able to use Rapids. Not only that, but it could be deployed on any of the most famous cloud providers like Amazon, Google Cloud, Microsoft Azure, and it seamlessly can scale from a single GPU to multiple GPUs with Dask support. So we hope that by the end of completing the workshop, you would have learned why Rapids is being built and how it fits in the data science ecosystem, and how to use GPUs for everyday advanced data science tasks. We hope that you will be able to learn how to get the next level performance from these common algorithms that you are already familiar with. By all of this, by applying all of these algorithms on a real world problem with real data. So this is what we want you, and we aim that you'll be able to gain by going through the self-paced workshop that I just provided you with access to. So before we wrap up the session today, I'd like to personally also invite you to attend our upcoming NVIDIA GTC conference, which is the AI conference for innovators, technologists, and creators. So I'm not sure if you're familiar with NVIDIA GTC. Well, NVIDIA GTC is more than the most attended, AI conference for developers. It is a global experience that brings together thousands of innovators, researchers, thought leaders every year, as well as decision makers who are shaping our world with AI and data science. So I also would advise you not to miss the inspiring keynote from NVIDIA's founder and CEO Jensen Huang, plus a wide array of sessions and talks from luminaries around the world. So go ahead, sign up for NVIDIA GTC. You can register for free. It is running from November 8 to 11 and learn how AI is actually transforming the world. In GTC, you will also have the chance to get hands-on experience with some of our instructor-led trainings provided by NVIDIA's DLI. And now in GTC, you will be able to attend some free workshops. These are 2 hours workshops that we are providing for free, as well as the more advanced full-day workshops for a very, very nominal conference pass. Now, spots are really limited for these workshops. If you are interested, go ahead, register and reserve a spot for you as soon as I can, because we're only receiving registrations on a first come first serve basis. So this is a great opportunity for you to get hands-on experience with an industry level courses and workshops that will be provided during GTC. I also would like to inform you about our DLI programs for educators. So if you are a qualified faculty, if you are a qualified researcher, I'd like to let you know that you can get certified to become a university and ambassador with NVIDIA. And this will allow you to teach DLI workshops to your university students or researchers or faculty at no cost. Now, we have already the DLI ambassadors in several universities in the world, like Arizona State University, Stanford, MIT, and many others. And I also would like to inform you and tell you about the teaching kits that are provided by the Deep Learning Institute. So qualified university educators can actually have access and download courseware, complete courseware on topics including deep learning, accelerated computing, robotics, data science, graphics, and Omniverse. And these kits include lecture material, hands-on laboratories, projects with solutions, as well as free cloud resources that provide free access for the students to access GPUs in the cloud in order to carry out the hands-on labs. So even if you don't have a physical lab in your university, you can still give these courses with the available free GPU credits that will be provided for your students. So please, if you want additional information, go ahead and go to nvidia.com training/educator programs to learn more about these teaching kits and how they are being adopted across the world in top universities in order to teach students state of the art in these domains. There's also additional resources that you may have access to. We have this new book titled Deep Learning by Magnus Ekman. You may look at these different sites or you may look at some of our free self-paced online courses. So if you'd like to get online courses, and you can complete them for free by going to and exploring some of these offerings, also available on our NVIDIA Deep Learning Institute's website. So please go ahead and explore them. So with that, I'd like to thank you all for attending, and thank you very much. If you have any questions, please type it in the chat. I'll be very happy to receive your questions. So back to you, Hannah.
Thank you very much, Dr. Manal. Can everyone please give a warm round of applause to Dr. Manal for such an insightful and wonderful session. And I saw in the chat that someone actually said that your introduction alone just captured the attention, and I agree. That was a very, very fantastic session, and I definitely will check out NVIDIA after this.
Thank you very much. Thank you. I'm really glad to be here with you guys, and I'm really, glad to have had the chance to share this with you, and looking forward to see you again in the future.
Thank you. Are there any final comments or questions before we move on to the next section, attendees? Dr. Manal, looks like there aren't any questions, just final comments on people saying thank you. And once again, thank you very much. I think we can move on to our final session, which is our, our breakout sessions. So if people still do have, I think, questions, then they can ask you during this time.
Yeah, Dr. Manal, are you still with us?
Yes, I'm here.
Okay, great. Because what I don't know how much time you have left. Thank you very much for presenting to us. What we have scheduled we actually have 15 more minutes, but I guess we could, I don't know if we want to take a break and then come for our breakout session, but we could have the breakout session set up right now. And if anyone wants to maybe take a few minutes to talk to you one-on-one, maybe you could enter one of the breakouts. The way we've been working with this is that after the sessions, the participants are able to maybe have a bit of more interaction one-on-one with the presenters in a breakout room.
Yes, for sure. Yes, for sure. So I'm here. Please go ahead and I'll be happy to join any breakout session if needed.
All right. So Gabriel, I think you can go ahead and set them up and then people can join at their leisure. Back to you, Hannah.
In the meantime, while we're still waiting for the breakout sessions, perhaps people can comment on and just speak on the experience that they've had for the sessions that were provided for the day. So does anyone have any key, takeouts from the sessions to say that based on everything I've learned today, this is something that I'm going to definitely apply?
I've created the rooms. Someone is at liberty to join any room.
Okay, thank you so much, Mr. Gabriel. So all the participants that want to join the specific breakout rooms, just to have one-on-one sessions with the specific presenters, can join the breakout rooms. So the people that were, the presenters can also join the various record rooms based on what they were presenting.
So, Dr. Manal, I think your session is the one labeled live instructor-led workshop.
Yes, I'm having difficulty joining it actually. So I'm trying to join it. I'm trying to join the instructor-led workshop breakout room.
They asked Gabriel what the issue could be. Okay.
Yeah, I'm not sure why I can't join it.